Hello there and welcome to Physics with William, where curiosity settles in for the evening and science is allowed to take its time. Tonight we are going to ease into one of the strangest ideas in all of cosmology, and one that sounds at first like it should be impossible. The topic is this: space itself can stretch faster than light. That sentence has a way of making the mind sit up a little straighter. Faster than light. Space stretching. Already it sounds like someone has smuggled a paradox into the room and is pretending not to notice. And yet this is not a trick of wording, and it is not some fringe idea that physicists whisper about only after the conference coffee has gone cold. It sits right at the heart of how we think the universe behaves on the larger scales. Before we wander any farther into that enormous question, I would love to know where you're listening from tonight and what the hour is in your corner of the world right now. It feels fitting somehow, because we are about to talk about the universe getting bigger while we ourselves sit in one small place, perhaps under a blanket, perhaps with a cup of tea, perhaps wondering whether the cosmos really needed to make everything this complicated. If this kind of slow scientific ramble is your sort of thing, and if you find it soothing or simply enjoy letting these ideas drift by for a while, then do consider liking the video and subscribing. It helps this calm little corner of science find the people who might need it most, especially those who enjoy a mystery that is large enough to make everyday worries feel at least a bit smaller. Now then, let us begin gently, because the subject deserves a slow start. It is very easy to hear the phrase faster than light and immediately think that something somewhere must be breaking the rules. After all, one of the first big ideas many of us learn about modern physics is that nothing can travel faster than light in empty space. That rule has become almost legendary. It appears in documentaries, in classrooms, in science fiction, and in the sort of conversations that begin with someone saying, "I am not a physicist, but..." Light speed has the reputation of being the ultimate limit, the great cosmic speed sign, the universe politely but firmly informing us that this far and no farther is how fast things are allowed to go. So when astronomers tell us that distant galaxies can appear to rush away from us faster than light because space itself is expanding, it sounds like the universe has contradicted itself before we have even had a chance to ask a follow-up question. One part of physics says no, faster than light, thank you very much. Another part seems to wave from the back of the room and say actually entire regions of the universe are separating from one another at astonishing rates. It is enough to make a person wonder whether the cosmos has simply changed the rules halfway through the game, which would be rude, though not entirely out of character. The good news is that the contradiction is only apparent. The rules are not being broken. But to see why, we have to do something that science often asks of us. We have to let go of the most natural first picture that forms in the mind. Because most of us, when we think about things moving apart, imagine objects travelling through space the way cars move along a road, or ships cross a sea. One object starts here, another starts there, and the distance between them grows because one or both are in motion. That picture works beautifully for everyday life. It works for footballs, bicycles, trains, spilled groceries rolling in opposite directions across the kitchen floor. It even works for planets orbiting stars and stars moving through galaxies. But the universe on the larger scales is not always playing that same game. Sometimes the distance between things increases not because the objects are charging through space at outrageous speeds, but because the space between them is itself changing. That sounds subtle at first, almost annoyingly subtle, as though physics is trying to win an argument by changing one word in the middle of the sentence. Yet that difference turns out to matter enormously. It is the difference between a runner sprinting down a track and the track itself quietly lengthening while the runner is still standing there. It is the difference between crossing a room and discovering that the room has decided, for reasons of its own, to become a hall. And I think that is where some of the fascination begins. Space is not just a passive emptiness, not just a blank stage on which matter performs. In modern cosmology, space can change. It can curve, it can stretch, It can carry galaxies farther apart without those galaxies having to behave like tiny cosmic race cars with their engines stuck wide open. That is already a peculiar idea if you stop and really sit with it. We spend most of our lives treating space as the fixed background to events. We walk across it. We place things in it. We measure rooms and roads and fields and say, here is the distance from one point to another, as though that distance is just sitting there minding its own business. Cosmology comes along and says not necessarily. On the larger scales, the background itself is dynamic. It is not just where things happen, it participates. There is something almost mischievous about that. It is as if we had spent centuries studying the furniture in a house, only to discover that the floorboards themselves are shifting beneath everything. Not violently, not in a way that throws your lamp into the ceiling, but steadily, relentlessly, and on such vast scales that whole galaxies can be carried apart by the changing geometry of the universe. And if those galaxies are far enough apart, the rate at which the distance between them increases can exceed the speed of light. Not because either galaxy is locally speeding through its own patch of space faster than light, but because the amount of space in between is growing. That distinction is going to be our quiet companion throughout this journey. Nothing locally outruns light through space in the forbidden sense, yet the distance between remote regions can still increase faster than light, because space itself is not constrained in quite the same way as objects moving within it. It is one of those ideas that looks at first like a loophole, and then slowly reveals itself to be something deeper than that. Not a cheat, not a technicality. A genuine feature of how the universe is built. Of course, this raises another question almost immediately. If space can do that, why does it not do it here in any obvious way? Why does your bedroom not expand overnight until your bookshelf drifts into the next postal code? Why do atoms not swell? Why do people not notice their coffee table receding during breakfast? And why does the cat still manage to sit in exactly the same inconvenient spot on the sofa, instead of being gently carried away by cosmological expansion? These are sensible questions, and they remind us that the universe is not simple, even when it is consistent. Expansion does happen, but not in the same way at every scale. Gravity, electromagnetism, and the other forces that bind structures together are more than capable of resisting that large scale stretching in local systems. Galaxies, solar systems, planets, chairs, teacups, and mildly offended houseplants do not simply get dragged apart because the cosmos is expanding. The effect that dominates on the grandest scales does not necessarily rule the smallest ones. There is a comfort in that, I think. The universe may be wildly dynamic, but it is not careless. It does not tug indiscriminately at everything all at once. It leaves local order intact while reshaping the larger picture. That larger picture, though, is where things become astonishing. For the universe is not merely filled with galaxies moving away from one another like fragments from some ancient explosion. That image, common though it is, can mislead. It suggests matter blasting outward into pre-existing emptiness, as though the Big Bang were a firework launched into a black sky. The modern picture is stranger, and in some ways more difficult to picture at all. The expansion of the universe is not debris flying into space. It is space itself changing everywhere at once. There is no central point in ordinary space from which everything is fleeing. There is no favoured location from which one could stand back and watch it all unfold. Every observer in a typical galaxy sees distant galaxies receding. The expansion is woven into the structure of the cosmos itself. That is one of those facts that can make a quiet room feel even quieter. Every galaxy, looking out on the universe, finds the distant universe pulling away. Not because that galaxy is special, not because it sits at the centre, but because this is what expanding space looks like from anywhere within it. It is a beautifully democratic sort of strangeness. No VIP seating, no cosmic balcony, just countless observers, if there are observers, each discovering that the vastness beyond them is stretching. And now we begin to approach the sharper edge of the puzzle. If distant galaxies can recede faster than light, does that mean light from some places can never reach us? Does the expanding universe place limits not only on travel, but on knowledge itself? Are there regions so remote that they are, in a practical sense, lost beyond the reach of observation, their light forever struggling through a space that keeps stretching faster than the light can cross it? The answer, perhaps unsurprisingly, is yes, and that is where the subject becomes not just a matter of speed but of horizons. The universe does not merely have distances, it has limits to what can ever be seen, not because the cosmos is hiding anything out of spite, but because the geometry of expansion creates boundaries for observation. That thought can feel a little unsettling. We are used to ignorance that can in principle be corrected. If something is too far away, build a better telescope. If something is too faint, wait longer. If something is blocked, move around it. Cosmology occasionally presents a harsher sort of limitation. Some things are not merely hard to reach or hard to detect. They are beyond what the structure of the expanding universe allows us to access. There are parts of reality from which light may never arrive, not because the light is too weak or the instruments too crude, but because the fabric of space between here and there is changing in a way that keeps the signal from ever completing the journey. And yet, I do not find that bleak. Strange, yes. Humbling, certainly, but also oddly clarifying. It reminds us that the universe is not designed around human convenience. It is under no obligation to fit neatly into our intuitions. If anything, the history of physics has been a long and patient lesson in learning that reality is often more subtle than the first image the mind offers. The Earth is not still. Time does not pass the same for everyone. Gravity is not just a pull, but a curvature. And now, space is not merely empty room. It can stretch, and in stretching it can carry galaxies apart fast enough to make the phrase faster than light sound less like a violation and more like a clue. There is also something satisfying about how this topic forces us to be precise with language. In daily life, words do a lot of heavy lifting without complaint. We say moving away, and usually that is good enough. But in cosmology, one has to ask moving through what, measured how, compared from where, and under which assumptions. Scientific progress often depends on exactly that sort of careful untangling. A phrase that sounds alarming at first can become perfectly sensible once the concepts inside it are separated and examined. Faster than light is one of those phrases. It triggers all the right instincts, then asks us to refine them. This is where the subject becomes more than a curiosity. It turns into a lesson about how science works when reality refuses to match intuition. We do not throw out the evidence because it sounds odd. We sharpen our understanding until the oddness becomes intelligible. That does not always make it feel ordinary. I'm not sure expanding space will ever feel entirely ordinary, and perhaps it should not. But intelligible is enough. Clearer is enough. Sometimes the greatest relief in science is not that the universe becomes less strange, but that its strangeness becomes coherent. So, as we settle into this larger story, it may help to keep one simple contrast in mind. There is the motion of things through space, and there is the change of space itself. Those are not the same. Much of the mystery ahead lives in that gap. A galaxy can sit relatively still in its local region and still find itself ever farther from another distant galaxy, because the intervening space grows. Light, meanwhile, continues to behave locally as light always does, moving through each small region of space according to the familiar rules. But when enough expanding space lies along the route, even light can find the journey working against it on the larger scales. All of this means that to understand why space can stretch faster than light, we first need to become comfortable with what it means for distance itself to change. Not because an object is racing away in the ordinary sense, but because the metric of the universe is evolving. That word metric can sound a bit formal, but the idea behind it is almost plain. It is the rule by which distance is measured. Change the geometry, and you change what distance means over time. In an expanding universe, the map is not printed once and left alone. The scale of the map is shifting while you're using it. And that is probably the place to move next, because once we stop imagining expansion as ordinary motion and start treating it as a change in the structure of space, several confusions begin to loosen. The faster-than-light problem looks different. Hubble and the recession of galaxies begin to make more sense. The image of the expanding universe becomes less like an explosion in a room and more like something subtler, stranger, and a good deal more accurate. We can then ask the next sensible question, which is what it really means for distance itself to grow, and why that growth does not place every galaxy on trial for breaking Einstein. To make sense of how space can stretch faster than light, we need to spend a little time with a quieter and more basic idea, because most of the confusion begins long before anyone mentions Einstein. It begins with the way we imagine distance. In ordinary life, distance feels simple. The gap between your chair and the wall is just there. The road between two towns is just there. The space between Earth and the Moon may be larger and more dramatic, but it still feels like the same kind of thing, a separation that exists whether anything happens or not. We picture space as a stable container, and then we picture objects moving around inside it. That habit is so natural that it takes some effort to notice we are doing it. But on the scale of the universe, that picture is not always good enough. Cosmology asks us to entertain something less familiar. The distance between two faraway galaxies can increase, not because those galaxies are pushing through space like swimmers cutting across a lake, but because the space between them is itself increasing. The container is not staying still. The stage is not rigid. The geometry that tells us what counts as a certain distance is changing with time. This is one of those ideas that can sound suspiciously like wordplay the first time you hear it. Space itself is expanding. Fine, you might say, but what does that actually mean? Is more emptiness being created? Are galaxies being dragged along? Is there some gigantic cosmic stretching machine working behind the scenes with a terrible maintenance record? Not quite, though I admit the image has charm. What it means in practice is that when cosmologists describe the large-scale universe, they find that the distances between widely separated galaxies increase in a systematic way over time, even when those galaxies are not powering away from one another through their local regions of space in the usual sense. This matters because the phrase moving apart can describe two different situations that look similar at first and are profoundly different underneath. In the first situation, objects move through space. A car drives down a road, a rocket leaves a planet, a comet sweeps through the solar system. In the second situation, the amount of space between distant objects grows. The objects can remain more or less at rest relative to the space immediately around them, yet the total separation still increases because the intervening space changes. If we treat those as the same thing, the whole subject becomes muddy very quickly. One reason the distinction is hard to grasp is that everyday experience offers almost no direct analogue. Rooms do not expand between breakfast and lunch. Streets do not silently lengthen during your commute, though some traffic jams create the emotional impression that they might. Local structures around us are held together too firmly for cosmic expansion to show up in a direct and dramatic way. The forces that bind matter into atoms, molecules, people, planets, and galaxies are strong enough that the overall expansion of the universe does not pull these systems apart. So our instincts are trained in a world where space seems steady and only the objects inside it move. That is why people often reach for analogies. Some of them are useful if handled carefully. The famous balloon analogy is one example. Imagine dots drawn on the surface of a balloon. As the balloon inflates, every dot gets farther from every other dot. No single dot needs to crawl across the rubber. The surface itself stretches, and the distances grow. From the point of view of a creature living only on that surface, it would look as though all the other dots were moving away. That captures something important. The recession is built into the stretching of the underlying geometry. not into the dots driving themselves around like tiny determined tourists. Still, every analogy comes with warning labels, and this one is no exception. The balloon surface is a two-dimensional surface expanding into a larger surrounding space, but the universe does not need an outside room to expand into. That is one of the most common points of confusion. People hear that the universe is expanding and quite reasonably ask what it is expanding into. The answer is that it does not need to be expanding into anything external in the way an inflating balloon expands into the air around it. The expansion happens as part of the geometry of space itself. There is no requirement for an outer warehouse full of spare emptiness waiting to be filled. That can feel unsatisfying at first because human intuition likes containers. We're used to asking where something is happening. Where is the universe located? Into what is it growing? What lies beyond it? These are understandable questions, but they may not all have meaningful answers in the way the mind expects. If space itself is the thing whose geometry is changing, then asking what the universe expands into can be like asking what lies north of the North Pole. The question sounds grammatical, it borrows the right words, but it may be importing assumptions that do not apply. Another analogy people use is raisin bread. Picture dough rising in the oven with raisins embedded in it. As the dough expands, each raisin sees the others moving away. The farther apart two raisins are, the more dough there is between them to expand, so the faster their separation increases. That feature makes the analogy especially useful, because it hints at something central in cosmology. On large scales, the recession speed between galaxies tends to increase with distance, not because distant galaxies are uniquely energetic, but because there is simply more expanding space between here and there. More gap means more total growth of the gap. Again though, the analogy is not perfect. Real galaxies are not raisins sitting passively in dough, and the universe is not a loaf in a kitchen waiting to be sliced. But it does help with one very important point. When distance itself grows, the effect accumulates over large separations. A modest rate of expansion per unit of distance, when multiplied across enough cosmic real estate, can produce a very large total rate of recession. That is how you eventually get to the startling statement that extremely distant galaxies can recede faster than light. Not because they are locally outrunning light in their own neighbourhoods, but because the overall separation across an enormous span of expanding space increases at that rate. At this stage, it helps to be very precise about what we mean by distance. There is the distance you might measure if you could somehow freeze the expansion of the universe at a particular moment and lay down a cosmic measuring tape from one galaxy to another. Then there is the history of how light travels between those galaxies, while the intervening space continues to expand during the journey. These are not the same problem. In an expanding universe, even defining distance becomes a bit more subtle than it first appears. It is not that physicists are being difficult for sport. The universe genuinely forces extra care on us. Suppose you imagine two galaxies very far apart, each more or less at rest with respect to the large-scale expansion. Cosmologists often say they are being carried along with the expansion, which is a helpful phrase so long as we do not take it too literally. They are not bobbing on a fluid. There is no invisible wind. The idea is simply that they share in the overall large-scale pattern of the expanding universe. Their separation changes over time because the scale of space changes over time. In that sense, they are not blasting through the cosmos under their own engines. They are participating in the evolving geometry. This is where people sometimes ask whether space is really a thing if it can expand. That is a fair question, and physics does not require us to imagine space as a substance in the everyday sense. It is not a gas, not a liquid, not a fabric you could pinch between finger and thumb if only you had very large hands. When physicists speak of the geometry of space, they mean the structure that determines distances, paths, and how objects and light propagate. In general relativity, geometry is not just bookkeeping. It is part of the physics. Space and time are dynamic. They can respond to matter and energy. They can evolve. So saying that space expands is a way of saying that the large-scale metric structure of the universe changes such that the distances between widely separated comoving points increase. That last phrase may sound a bit formal, but the idea behind it is straightforward enough. Think of choosing a set of cosmic reference points that move along with the general expansion, rather than cutting across it. If two galaxies are approximately comoving in that sense, then their coordinates in the expanding grid remain steady, while the physical distance between them grows as the scale of the universe grows. It is rather like placing pins in a sheet that is being stretched. The pins keep the same addresses in the pattern of the sheet, yet the distance from one pin to another becomes larger as the sheet expands. This helps explain a point that often seems contradictory the first time around. A galaxy can be at rest in one meaningful sense and still be getting farther away from us. At rest relative to its local patch of the expanding universe does not mean maintaining a constant distance from every other faraway galaxy. Distance is changing because the background geometry is changing. Once that clicks, a lot of the apparent paradox starts to loosen. It also helps us avoid a misleading picture of the Big Bang. Many people grow up with the idea that the Big Bang was an explosion in space. Something violent happened at one central location, and matter flew outward into the emptiness. That image is understandable, because explosions are familiar, but it points in the wrong direction. The Big Bang was not an explosion into pre-existing space from a privileged centre. It was an early hot dense state of the universe, followed by expansion of space itself. Every region of the observable universe was once much closer together. The expansion happened everywhere. There is no centre of the expansion within the ordinary three-dimensional space of the universe, just as there is no special centre on the surface of an inflating balloon if you restrict attention to the surface itself. The absence of a centre is more than a curiosity. It is one reason every observer in a typical galaxy sees other distant galaxies receding. If you are in one galaxy, it can feel as though everything is moving away from you, which might briefly encourage delusions of cosmic importance. But an observer in another distant galaxy sees much the same pattern. This is not because everyone is at the centre. It is because in a homogeneous large-scale expansion, recession is built into the stretching of space everywhere. The pattern is not evidence of a special location. It is evidence of a special kind of geometry. Now, a sensible person might ask whether there is any actual evidence for this way of thinking, or whether cosmologists simply became too attached to balloons and baked goods. There is evidence, and it is substantial. The large-scale recession of galaxies, the systematic redshifting of their light, the observed relation between distance and recession, the cosmic microwave background, and the success of models based on an expanding universe all point in the same direction. The language of expanding space is not decorative. It is part of the framework that makes sense of the observations. Even so, one should be cautious. Physicists sometimes debate how literally to phrase expanding space, because language can nudge intuition in helpful or unhelpful ways. Some prefer to emphasize the changing geometry rather than imagine space as an active medium doing the stretching. Others find the stretching language useful so long as its limits are understood. That is normal in science. We often rely on pictures that are accurate enough to guide understanding without mistaking them for little movies of reality playing behind the scenes. The important thing for us is not to turn the language into mythology. Space is not some goo. Galaxies are not helpless beads in syrup. The universe is described by a mathematical framework in which the large-scale distances between comoving galaxies increase over time. That is the clean statement underneath all the analogies. Once you accept that, the next step is to notice what happens when the distance is already very large. If a little bit of expansion applies across every chunk of the gap, then a very long gap can grow very quickly in total. That is the whole secret, quiet but powerful. But imagine a long road that gains a tiny bit of new length in every mile. If the road is short, the total added length is small. If the road runs across a continent, the total added length can be enormous. Cosmological expansion works in a somewhat similar way. The farther away a galaxy is, the more expanding space lies between us and it. and so the faster the total recession can be. Nearby galaxies may drift apart relatively slowly in cosmic terms. Very distant ones can recede at astonishing rates. Push far enough, and the recession rate exceeds the speed of light. At this point, the nervous system of anyone who has ever heard the phrase "nothing" can go faster than light may begin to twitch. Quite right too, it sounds dangerous, but notice what has and has not been said. We have not said that a galaxy near us can locally accelerate through its surrounding space past a beam of light. We have not said that in a local laboratory you could watch a rocket overtake light and send Einstein into early retirement. We have said that the distance between remote galaxies can increase faster than light because of the expansion of space across the gap. That is a different statement, and the difference is everything. Light itself also gets caught up in this story in a subtle way. When light travels across the expanding universe, the stretching of space affects the light wave, increasing its wavelength. This is what we call cosmological redshift. It is not quite the same as the ordinary Doppler effect you hear when an ambulance passes and the pitch changes. The two are related in spirit, but in cosmology, the redshift reflects the stretching of space during the light's journey. The light is not merely emitted by a source moving through static space. The space through which it travels is evolving, and the light is stretched along with it. That means the expanding universe is not just changing where things are, it is changing how signals move across the cosmos and what those signals look like when they arrive. Light from very distant galaxies reaches us more stretched, more redshifted, carrying a record of expansion written into its own wavelength. In a sense, the universe leaves notes in the light and then waits billions of years for us to learn how to read them. There is something pleasantly humbling about that. We do not stand outside the universe measuring it with a ruler as one might measure a fence. We infer its behaviour by the light that reaches us, by the patterns in that light, by the consistency of the laws of physics, and by the theoretical structures that tie the observations together. Cosmology is an act of patient reconstruction. We look, we compare, we model, and slowly a coherent picture emerges, though not always one that flatters our instincts. So when distance itself begins to grow, the change is not just quantitative. It changes what it means to ask how far away something is, how fast it is receding, whether its light can reach us, and what sort of speed limit applies. It replaces the simple stage of everyday intuition with a dynamic one. The universe stops looking like a fixed box full of moving objects and starts looking like an evolving geometry in which motion and expansion must be carefully distinguished. That distinction is the key that opens the next door. Because once we see that recession, due to expansion, is not the same thing as motion through space, we are finally in a position to ask the more pointed question without getting tangled in the wording. If nothing can move through space faster than light, why exactly does the expansion of space not count as breaking that rule? Or to put it another way, where does Einstein's limit really apply, and where does it not? If space can stretch so that very distant galaxies end up separating faster than light, then it becomes especially important to understand what the famous speed limit actually says, because the rule is often repeated in a shorter and blurrier form than physics really intends. We hear that nothing can go faster than light, and it sounds simple enough. It sounds like the universe has posted one clear sign and the matter is closed. But like many famous scientific statements, it means something very precise, and most of the confusion begins when that precision gets sanded away. The rule is not simply that fast things are forbidden. It is not a cosmic traffic law written by a stern committee somewhere beyond the stars. The deeper point is that in the structure of relativity, light speed marks the limit for how influences, signals, causes, and objects with mass can move through their local region of space and time. That word local is doing a great deal of work and it deserves our attention. Physics is often at its clearest when it speaks about what nearby observers can measure in their immediate surroundings. In that setting, the laws are crisp. Light in empty space has the same speed for every local observer. No massive object can be accelerated through space to match or exceed it, because must come before effect in a way that all observers can consistently preserve. These are not separate little rules taped together. They're expressions of the same underlying structure. To see why this matters, it helps to step back from the slogan and ask what would actually go wrong if ordinary objects could move through space faster than light. At first, the answer might seem to be not much. Perhaps a spaceship would simply be very fast. Perhaps messages would arrive sooner. Perhaps interstellar travel would become less inconvenient, which many of us would welcome, especially if it reduced the sort of travel time that makes even a packed lunch feel existential. But relativity is not bothered by inconvenience. It is bothered by inconsistency. Once faster-than-light motion through space is allowed in the ordinary local sense, the neat relationship between space, time, and causality begins to come apart. One of Einstein's great achievements was showing that space and time are not separate fixed containers, but part of one interwoven structure. Different observers moving relative to one another do not agree on every detail of distance and duration. They can disagree on how long something takes or how far apart two events are. Yet the laws of physics remain consistent because they share a deeper structure, and within that structure light speed is a boundary. It is the same for all local observers. That constancy is not a quirky add-on. It is the thing that forces space and time to adjust so the laws stay the same. Time can dilate, length can contract, simultaneity can depend on motion, but the speed of light remains fixed. This means that light is not just one fast thing among many. It occupies a very special role. It is woven into the geometry of space-time itself. It defines the boundary between events that can influence one another and events that cannot, at least not yet. If you picture an event as a point in space-time, then the future that can be reached from it by light or anything slower forms a kind of causal region. The past that could have influenced it forms another. Outside those regions lie events too far away in space-time for a light signal to connect them in time. That causal structure is one of the most basic features of relativity. It tells the universe which events can talk to, which others without contradiction. If something could move faster than light through space in the ordinary local sense, it could slip outside that structure. In one frame of reference, it might appear to travel forward in time from cause to effect. In another frame, because different observers slice space-time into space and time differently when they are in relative motion, the order could reverse. An effect could appear before its cause. A reply could arrive before the message was sent. A warning could be received before the danger that inspired it. The problem is not merely that this sounds odd. The problem is that it opens the door to logical loops that make the idea of physical explanation unstable. Imagine sending a faster-than-light message to a distant spacecraft. In your frame, you send it at noon, and it arrives shortly after. But because of how relativity mixes space and time for observers in relative motion, another observer could judge the arrival to happen before the sending. If the spacecraft then immediately sends a faster-than-light reply back, there are arrangements where you receive the reply before you ever sent the original message. Now the fun begins, though it is the sort of fun that makes physicists squint. What if the reply says, "Do not send the message. If you obey it, you never send the original. If you never send the original, the reply has no reason to be sent." One can dress this up in spaceships and clocks and very serious diagrams, but the basic difficulty is plain enough. Faster-than-light local signalling threatens causality. This is why the light speed limit is not merely about engineering, or about photons having an unfair advantage. It protects the coherence of the universe. It keeps the order of cause and effect from becoming dependent in a disastrous way on who happens to be moving relative to whom. Relativity allows many things to become relative. It does not allow the structure of physical explanation to collapse into contradiction. There is another side to the limit, and it concerns energy. Even without stepping into the full philosophical thicket of causality, the laws of relativity tell us that accelerating an object with mass closer and closer to light speed becomes harder and harder. Not just difficult in the ordinary way, like pushing a heavy sofa up a staircase while reconsidering your life choices. Harder in a way that grows without bound. Each additional gain in speed demands more energy than the last. The closer you get to light speed, the more extreme the demand becomes. The theory does not say that engineers need a slightly bigger fuel tank. It says there is no finite amount of energy that will carry a massive object all the way to light speed. That feature is not some arbitrary technical nuisance added to keep things dramatic. It reflects the geometry of space-time and the way momentum and energy behave in relativity. Massive particles can move arbitrarily close to light speed if you pour in enough energy, though in practice the obstacles are enormous. But the exact speed of light is not something they can reach by acceleration. It is a boundary, not a milestone. Light itself, along with other massless particles, lives on that boundary naturally. It does not need to be pushed up there. It is simply how such particles move in empty space. Massive objects live beneath it. They may approach, but they do not cross. This is another point where language can mislead us. People sometimes speak as though an object gets too heavy to reach light speed. That phrasing has historical roots, but it can muddy the waters if taken too literally. The cleaner way to think about it is that the energy required to keep accelerating a massive object toward light speed grows without limit. The theory does not provide a smooth bridge from ordinary sublight motion to faster-than-light motion for things with mass. It builds the speed of light into the structure of what motions are physically allowed. Light then is strange in a very specific and elegant way. From our point of view, it races across space at the maximum speed. Yet from the internal logic of relativity, it is not simply winning a race. It is tracing out the paths permitted to massless entities by space-time itself. That is why all local observers, no matter how they move, measure the same value for its speed. This sounds impossible until one accepts the price the universe charges for it. Space and time themselves are not absolute. Distances depend on motion. Durations depend on motion. Simultaneous for one observer does not always mean simultaneous for another. These adjustments are not quirks. They are the bookkeeping that keeps light speed fixed for everyone. Once you see that, the rule begins to feel less like a prohibition and more like a statement of architecture. The universe is built in such a way that local motion through space has a maximum causal speed, and that speed is the speed of light in vacuum. Objects with mass can move slower than that. Massless particles move at that. Nothing locally travels faster through its own nearby patch of space-time without tearing up the causal furniture. All of this can sound rather grand and remote, until we remember that it is not merely theoretical decoration. These effects have been measured over and over again. Particles accelerated in colliders behave according to relativity. Their lifetimes stretch in motion. Their energies and momenta follow the relativistic rules. Muons created high in the atmosphere survive to reach the ground because time for them passes differently, relative to us while they move at enormous speed. Clocks flown on aircraft or carried by satellites do not tick in quite the same way as clocks on the ground. The technology that lets a phone guide someone through a city depends on correcting for relativistic effects. The speed limit is not a slogan floating above the world. It is built into phenomena we can observe and into systems we use. Even so, one of the easiest mistakes to make is to imagine the speed limit as if it were a property of light alone, as though light happened to be the fastest thing available, and everything else is merely slower by bad luck. In fact, the relationship runs the other way. Light travels at the invariant speed because that speed is already built into the structure of space-time. If there were no photons, relativity would still contain that speed as a fundamental feature. Light reveals the rule, it does not invent it. Now, this brings us to a subtle but crucial point. When physicists say nothing moves through space faster than light, they mean through space in the local sense that relativity governs so strictly. They mean in your local neighbourhood, where measurements can be made by nearby observers with clocks and rulers, the laws take their special relativistic form. In that domain, the limit holds absolutely. A spaceship cannot zoom past a beam of light right beside it. A signal cannot leap ahead of causality in a local laboratory. The speed limit is not optional there. But the universe as a whole is not always described by special relativity alone. On the larger scales, we need general relativity, which allows space-time itself to be curved and dynamic. And once space-time becomes dynamic, one has to be careful not to smuggle local rules into global situations without checking whether they apply in the same way. This is the trap behind much of the faster-than-light confusion. People hear that very distant galaxies recede faster than light and instinctively treat it as though one galaxy is locally shooting past another in flat, unchanging space. That would indeed be a problem. But that is not what cosmology is claiming. It may help to notice how strongly our intuition wants all speeds to be comparable in a simple way. If one train goes east at one speed and another goes west at another speed, we add them. If one runner moves across a field, we ask how fast relative to the ground. If one airplane chases another, we calculate a closing speed. Everyday motion invites ordinary arithmetic. Relativity already complicates this locally, because even velocities do not add in the naive way near light speed. But cosmology goes further by changing the stage itself. Once the geometry between distant objects evolves over time, asking for a single simple speed between them becomes more delicate. Different notions of distance and rate of change can tell different stories, and not all of them correspond to local motion through space. That is why the speed limit needs its full sentence. Nothing with mass moves through its local region of space-time faster than light. No local signal outruns light. No local cause leaps ahead of its effect. Those are the sharp statements. They are what relativity protects. They are what experiment supports. They are also entirely compatible with the large-scale expansion of the universe, producing superluminal recession between sufficiently distant galaxies. There is a useful way to feel the difference, without yet diving into the full cosmological machinery. Imagine laying down a chain of observers between two very distant galaxies, each observer close enough to the next that special relativity works in the familiar local way. Each observer measures light moving past at the usual speed. Each one sees neighbouring objects behaving lawfully. Locally, the speed limit is never violated. Yet when you compare the total distance between the far ends over cosmic time, that distance can still grow faster than light, because you're no longer talking about one object racing through one local region. You are adding up the effects of expansion across many regions of space-time. The local rule survives untouched even while the global separation behaves in a way that sounds startling if described too casually. There is something satisfying in that. Physics is not getting away with a trick. It is being consistent at a deeper level than first impressions allow. The same theory that forbids local, faster-than-light motion is the one that permits an expanding universe with superluminal recession at great distances. The apparent contradiction comes from us, not from the equations. We hear the same phrase, faster than light, in two different contexts and assume it must mean the same thing both times. But it does not. This is also why no one has ever built an engine that simply pushes a massive craft through space beyond light speed using ordinary propulsion. It is not because we are still a little behind on the paperwork. It is because ordinary local motion is constrained by relativity itself. If one dreams of faster-than-light travel, one has to start dreaming about stranger possibilities, about changing the geometry, about shortcuts, about speculative structures that do not rely on a ship merely going faster and faster in the everyday sense. Most of those ideas remain hypothetical and deeply problematic. The basic limit on local motion remains intact. For now, though, the important thing is simpler. The universe has a local speed limit because space-time has a causal structure. Light marks that structure. Massive objects cannot be accelerated across that boundary. Signals cannot outrun it without threatening the consistency of cause and effect. Every successful test of relativity strengthens that picture. So when we later say that the universe expands in such a way that distant galaxies can separate faster than light, we are not withdrawing any of this. we are stepping into a different category. Not ordinary motion through space, but the changing geometry of space itself. And that is the exact distinction we need to keep in view next, because the phrase faster than light becomes much less alarming once we separate motion from expansion and stop treating the universe as though it were a static room with galaxies flying around inside it. That distinction is the hinge on which the whole subject turns, because motion and expansion can look similar from a distance, while being very different once you ask what is physically happening. If we do not separate them carefully, then every later step becomes harder than it needs to be. We start mixing local motion with global change, and before long the universe seems to be arguing with itself. It is not. We are just asking one idea to do the work of two. In ordinary life, motion is familiar. You walk across a room, a train leaves the station, a planet circles its star. In each case, something changes position relative to the space around it. We can point to an object, point to a location, and ask how fast the object is moving from one place to another. Even when the details get complicated, the picture itself stays recognizable. There is a background that feels steady enough, and there are objects changing position within that background. That is the kind of situation our intuition was built for. Expansion on the scale of the universe is stranger, because the background itself is not staying fixed. The distance between faraway galaxies can increase, even if those galaxies are not behaving like little rockets, blasting through the space around them. Their local situation can remain quite ordinary. A galaxy can sit in its own region of the universe without any dramatic sense of acceleration, without stars flying off one side and planets losing their grip, and yet that same galaxy can still become more distant from other galaxies, because the large-scale geometry of the universe is changing. The separation grows not because each galaxy is tearing through its neighbourhood in the usual sense, but because the amount of space between them is increasing. This is the point where the mind usually protests. It feels like a trick. If the distance is growing, then surely something must be moving. And in a broad descriptive sense, yes, something is changing. Galaxies are receding from one another, but the reason they recede matters. One case is motion through space. The other is the expansion of space. Those are not interchangeable descriptions. They lead to different conclusions about speed, about energy, about what relativity allows, and about why no rule is being broken when very distant galaxies end up separating faster than light. A useful way to approach this is to begin with a modest example, rather than the whole universe at once. Imagine a very long walkway made of separate rubber sections joined end to end. Now place two figures on it, one near the left side and one very far to the right. Suppose neither figure is walking. Each stands still relative to the patch immediately beneath their feet. If the walkway itself stretches, the distance between the figures increases, even though neither one is marching along the surface. They are not moving through the walkway in the usual sense. The walkway is changing. If you looked only at the growing distance, you might say they are moving apart, and that would not be wrong in ordinary language. But physically it would matter very much that the increase came from stretching of the walkway, rather than from the figures running. Now, as always, analogies must be handled with care. The universe is not a rubber walkway made by an over-enthusiastic engineer, but the example helps isolate the difference we need. Motion means an object changes position through a background. Expansion means the background that defines separation changes. Once the background becomes dynamic, describing the result only in terms of objects moving can become misleading. This is especially important because our habits of speech are so relaxed. We say a galaxy is moving away from us. Astronomers say it too because sometimes that phrasing is convenient. But if we hear only that sentence and bring ordinary intuition to it, we imagine something like a cannonball or a racing car, an object shooting through a pre-existing emptiness. That is where the trouble starts. The universe is not a fixed room full of galaxies all driving in different directions. On large scales, it is better described as a changing geometry in which the distances between galaxies evolve over time. There is a quiet consequence of this that often goes unnoticed at first. In ordinary motion, velocities can be compared locally. One car passes another, one spacecraft overtakes another. You can imagine them side by side and ask who is moving faster through the local space they share. In cosmology, when two galaxies are vastly separated, there may be no single, simple sense in which they share one common static background, against which a direct velocity comparison works in the everyday way. The universe between them is expanding. Space-time is curved and dynamic, so the statement that a distant galaxy is receding from us at some rate is not the same kind of statement as saying a nearby rocket passes our spacecraft at a measured local speed. This is one reason cosmology asks for more patience than instinct usually wants to give it. It is not enough to hear the word speed and assume all speeds are alike. There are local velocities measured by nearby observers. There are recession rates that describe how proper distance changes in an expanding universe. Those are related ideas, but they are not identical. If we collapse them into one blurry notion, then faster than light recession sounds like a violation. If we keep them separate, it becomes clear why the speed limit of relativity remains intact. Think again about the local situation of a galaxy. Inside that galaxy, stars orbit. Gas clouds move. Planets circle suns. If an observer there measures light in the vacuum of their local region, they get the same speed of light that any other local observer should. If they launch a spaceship, that ship cannot be accelerated through nearby space beyond that limit. The familiar rules of relativity apply perfectly well. Nothing about cosmic expansion suddenly gives local objects permission to misbehave. The oddness only appears when we look across very large distances and ask how far apart distant galaxies become over time, because the space between them grows. It may help here to contrast two pictures more directly. In the first picture, imagine dots moving across graph paper. The paper stays fixed. The dots glide over it. That is motion through a static background. In the second picture, imagine the dots staying on the same grid intersections while the grid itself gradually enlarges. Now the dots become farther apart even though they are not sliding across the paper in the same way. That second picture is closer to cosmological expansion. Again, not literally. The universe is not graph paper, but the logic is much better. Once you see that, another common confusion begins to ease. People often ask whether galaxies are being dragged through space by expansion, almost as if space were a river sweeping them along. That can be a tempting picture, but it can also lead to the wrong questions. It suggests that galaxies should feel some sort of cosmic wind, or that objects should be able to detect themselves being carried by the expansion in their local surroundings. That is not how it works. The expansion is not a local breeze, it is a large-scale property of the geometry of the universe. Nearby bound systems do not feel it in the way a leaf feels a stream. Gravity and other binding forces dominate locally, while expansion shows up in the increasing separations between sufficiently distant, unbound regions. So when we say a faraway galaxy is receding, we are not picturing stars inside it being blown backward, nor are we picturing the galaxy revving up its engines. We are saying that if we compare the large-scale structure of the universe at one time to that at a later time, the physical distance between galaxies that take part in the general expansion has increased. That is a geometrical statement before it is anything else. There is something else that makes this distinction hard to keep straight, and that is the way the universe presents itself to us observationally. We do not watch the whole cosmos from the outside. We receive light, we measure red shifts, we infer distances, we build models that explain the pattern. Because the evidence often comes to us through the language of recession, the ordinary idea of motion stays close at hand, but the interpretation of that recession is what matters. The light from distant galaxies is redshifted not merely because galaxies are running through static space like sirens passing on a road. On cosmic scales, the redshift is tied to the expansion of space during the light's journey. The wavelength is stretched as the universe stretches. That is another place where motion and expansion part company. In ordinary Doppler shift, a source moves through space relative to an observer, and the signal changes in a familiar way. In cosmological redshift, the changing scale of the universe itself contributes to the stretching of light. The difference is subtle when said quickly, but it is deep when followed carefully. Light travelling across an expanding universe does not simply cross a fixed arena. It crosses an arena whose geometry evolves while the light is in transit. This is why the phrase "the galaxy is moving away" can be both useful and dangerous. Useful because it captures the observed recession. Dangerous because it invites us to treat that recession as ordinary travel through a static stage. The more accurate picture is that large-scale distances evolve because the stage itself changes. It is worth pausing over how radical that is. Most of human experience takes place on scales where the geometry of space can be treated as stable enough. A field is a field. A road is a road. If two houses are 10 meters apart today, they will not become 11 meters apart tomorrow, because the universe decided to stretch the neighborhood overnight. Local binding wins. The expansion of the cosmos is far too weak on small scales to pry apart houses, planets, or even galaxies themselves. So our brains grow up in a world where motion means moving through a background and almost never means the background changing. Then cosmology arrives and asks us to imagine a universe where the large-scale background is dynamic. It is no wonder the first instinct is resistance. Still, the distinction becomes easier once we consider what each picture predicts. If galaxies were all simply flying through static space because of some ancient explosion, we might expect a center somewhere, a special place from which the outward rush began. We might expect the geometry of the universe to behave differently than it does, but the observed large-scale pattern is much better captured by a model in which expansion happens everywhere. Every distant galaxy sees other distant galaxies receding in roughly the same general way. There is no privileged central seat. That is a hallmark of expansion of space, rather than debris flying into emptiness from one favoured location. The difference also shows up in how recession depends on distance. In an expanding universe, the farther away a galaxy is, the faster its recession tends to be, because there is more intervening space to expand. That point is easy to say, and surprisingly powerful. A modest amount of expansion per unit of distance adds up over great spans. Nearby galaxies may separate slowly enough that the recession seems almost tame. Add enough billions of light-years of expanding space between two regions, and the total recession becomes enormous. This is how faster-than-light recession emerges naturally without any galaxy locally breaking relativity. One way to picture this without misleading ourselves too much is to imagine a line of tiny gaps, each one expanding just a little. If you have only a few gaps, the total increase is small. If you have a vast number of gaps, the total increase can be very large. No single gap needs to grow outrageously fast. The total separation becomes large because the small growth is distributed across an enormous stretch. In the same way, no galaxy needs to be locally outrunning light through its neighbouring space. The total distance to a very remote galaxy can still increase faster than light, because that increase is spread across all the expanding space in between. This is where people sometimes ask a fair and slightly sneaky question. If the distance to a very distant galaxy increases faster than light, does not that still mean light can never catch up? In some cases, yes, and that is part of what makes cosmic horizons so interesting. But the important thing for the present discussion is why this does not count as a local violation. Light always behaves locally in the usual way. In each small region it moves at the speed light should move. Yet if the total expanding distance ahead is changing in a certain way, the journey can become more complicated than a simple race across fixed terrain. A traveller can run at full allowed speed and still fail to reach a destination if the path itself is lengthening fast enough over the relevant scales. Notice again how different that is from ordinary motion. In ordinary motion through static space, if one object separates from another faster than a third object can travel, that sounds like a straightforward comparison of velocities. in an expanding universe, the comparison is not so simple because the underlying geometry participates. The path is not passive. Distance is not just waiting there to be crossed, it evolves. There is also a more subtle conceptual difference between motion and expansion that concerns reference frames. In special relativity, local inertial frames let nearby observers describe physics cleanly. Motion through space is defined with respect to such local structures. In cosmology, when speaking about the recession of very distant galaxies, we often use coordinates adapted to the expanding universe as a whole. Those coordinates are useful because they reflect the large-scale symmetry of the cosmos, but the velocities they suggest across enormous separations are not the same thing as local speeds measured in a shared inertial frame. This is one reason why superluminal recession is not alarming to relativists. It arises in a context where the naive everyday reading of velocity no longer applies. I realise that may sound a little technical, but the core idea is plain enough. Close by, the universe behaves locally like the special relativity we know and trust. Far across cosmic distances, space-time is curved and evolving, so global statements about separation require more care. You cannot simply lift an everyday notion of motion out of a local setting and apply it unchanged to the whole expanding universe. The reward for accepting this is that the puzzle becomes much more manageable. We no longer have to imagine galaxies cheating. We no longer have to invent hidden exceptions to Einstein. We simply recognize that motion through space and expansion of space are different physical situations. The light speed limit belongs to the first in the strict local sense. The second changes the distance between faraway objects through the evolving geometry of the universe itself. There is something deeply instructive in that, beyond this one topic. Physics often advances by showing that familiar words cover more than one situation. Weight feels obvious until gravity and acceleration must be separated. Heat feels obvious until temperature and energy flow are distinguished. Motion feels obvious until cosmology asks whether the object moves through the stage or whether the stage itself changes. The words stay the same, but the concepts underneath become more precise. And that precision matters especially when we turn from the conceptual picture to the historical evidence, because the idea that galaxies recede in a way tied to distance did not come out of nowhere. It was measured, it was argued over, it emerged from observations of galaxies and the light they sent across the growing universe. The distinction we have been building here is what makes those observations intelligible rather than contradictory. Once motion and expansion are no longer being blurred together, the next step is easier to appreciate. We can begin to see why Hubble found what he found, and why the quiet drift of galaxies turned out to be one of the clearest signs that the universe itself does not sit still. Once motion and expansion are no longer being treated as the same thing, the historical story becomes much easier to appreciate, because the idea of an expanding universe did not arrive as a philosophical mood or as a scientist trying to make the cosmos sound dramatic. It arrived through observation, through improved instruments, through careful measurement, and through a growing realization that the faint cloudy patches scattered across the night sky were not all nearby objects inside our own galaxy. Some of them were galaxies in their own right, immense systems of stars so far away that even the largest telescopes of earlier centuries had seen them only as soft smudges. That part is worth pausing over. For a long time, the universe was thought to be much smaller than the one we know today. The Milky Way was often treated as the whole show, or at least close to it. The fuzzy spiral shapes visible in telescopes were called nebulae, which simply means cloudy things, and that name reveals how incomplete the understanding was. Some astronomers suspected these spirals might be separate island universes, huge stellar systems beyond the Milky Way. Others thought they were smaller objects inside our own galaxy. The debate was not trivial, because it touched the size of the universe itself. If the spirals were nearby, then the cosmos remained relatively modest. If they were far away, then the universe was vastly larger than many people had imagined. The shift began with a kind of patient astronomical work that rarely sounds glamorous until one realizes what it changed. In the early 20th century, astronomers were learning how to estimate distances to stars and clusters using variable stars, especially a class called Cepheid variables. These stars brighten and dim in a regular way, and crucially, the period of that variation is linked to their true brightness. That relationship had been established by Henrietta Swan-Leavitt, whose work became one of the essential tools in modern astronomy. Once astronomers knew how bright a Cepheid really was, they could compare that with how bright it appeared from Earth, and infer the distance. It was a method of turning flickering starlight into a cosmic measuring tape. Edwin Hubble entered this story at just the right moment, armed with one of the most powerful telescopes in the world, the Hooker telescope at Mount Wilson in California. By the standards of its time, it was a giant. With it, Hubble examined the Andromeda Nebula and identified Cepheid variable stars within it. That was the crucial step. Once he measured their periods and estimated their true brightness, the conclusion was unavoidable. Andromeda was far outside the Milky Way, not a local gas cloud, not a small object tucked into our own stellar neighbourhood. It was another galaxy altogether. That discovery did more than settle one debate. It expanded the universe in the human mind long before anyone could say with confidence that space itself was expanding. Overnight, or as close to overnight as science ever gets, those faint spiral smudges became vast stellar systems scattered through an enormous cosmos. The Milky Way was no longer the universe. It was one galaxy among many. That alone is hard to overstate. It was one of those moments in science when scale changes so drastically that almost every prior assumption has to be re-examined. But the distances were only one side of the story. The other came from light itself, and here another astronomer deserves careful attention. Vesto Slipher had already spent years measuring the spectra of spiral nebulae. Spectroscopy may sound technical, but the basic idea is familiar enough. When light is spread into its component colours, it reveals patterns that tell us about the source. Dark lines appear where certain elements absorb specific wavelengths, and those patterns act like fingerprints. If the entire pattern is shifted toward the red end of the spectrum, it suggests the source is receding. If it is shifted toward the blue, it suggests approach. This is related to the Doppler effect, the same general principle that changes the pitch of a passing siren, though on cosmic scales the interpretation becomes more subtle, as we have already seen. Slipher found something remarkable. Many of the spiral nebulae showed redshifts. In plain language, their light suggested recession. A few objects showed blue shift, but the general pattern leaned heavily one way. Much of the distant universe seemed to be moving away. At the time, this was intriguing but not yet decisive, because the distances to those objects were still uncertain. Redshift without distance is a clue, not a full story. It tells you something about motion or recession, but not the larger pattern of the cosmos. What Hubble eventually did was combine distance estimates to galaxies with the redshift information, much of it measured by Slipher, and in the late 1920s he published the result that changed cosmology. The farther away a galaxy was, the greater its redshift tended to be. In practical terms, more distant galaxies were receding faster. That relation is now one of the basic pillars of observational cosmology. It told astronomers that the universe was not static on large scales. It was changing. The galaxies were not scattered through an eternal stillness. There was a systematic pattern in their recession. Now, one has to be fair to the historical details here. Hubble did not do everything alone, and science rarely belongs neatly to one pair of hands, no matter how textbooks like to tidy the narrative. Slipher's redshift measurements were indispensable. Leavitt's work on variable stars made the distance scale possible. Georges Lemaitre had already derived an expanding universe solution from general relativity, and had even connected recession with distance before Hubble's 1929 paper became widely known. The historical record is richer than the simplified version many of us first hear. Still, Hubble's observational work played a central public role in convincing the scientific world that the universe on large scales was not sitting still. There is something especially powerful about that, because the discovery did not depend on one spectacular event. No star exploded at the right moment to announce the answer. No cosmic sign lit up the sky reading this way to expansion. Instead, the case emerged from quiet patterns in light and distance. It was careful and cumulative. Measure the stars, identify the variables, estimate the distances, spread the light into spectra. Compare the shifts, build the relation, realize what it implies. It is a good reminder that some of the largest discoveries in science arrive not by noise but by consistency. The relation between distance and recession also had an important conceptual consequence. It did not look like random motion. If galaxies were simply flying through a static universe in every which way, one would not expect such a clean, large-scale trend. Some local motions certainly exist. Galaxies tug on each other gravitationally. Small groups and clusters have their own internal dynamics. Nearby galaxies can approach one another. The Andromeda Galaxy, for example, is moving toward the Milky Way rather than away from it because local gravity dominates their mutual behavior. That is an important detail because it prevents the story from becoming too simplistic. Not every galaxy is receding from every other galaxy under all conditions. Local structure still matters. But once one zooms out to large enough scales, the individual gravitational scuffles matter less than the overall pattern, and the pattern is clear. The universe is expanding. The more distant the galaxy, the faster the recession. That is exactly the sort of behavior one expects if space itself is stretching. More distance means more intervening space, and more intervening space means more total expansion across the gap. The observation did not by itself prove every detail of modern cosmology, but it provided the key observational fact that made an expanding universe unavoidable. It also changed how astronomers thought about the past. If galaxies are moving away from one another now, then earlier in cosmic history they must have been closer together. Run the film backward in the mind and the universe becomes denser and hotter. This is one of the reasons Hubble's discovery did not remain a mere cataloguing result. It opened a time dimension to cosmology. The universe had a history. Not just a distribution of objects in space, but an evolving large-scale state. The sky became evidence of change over time, not just arrangement. That idea can feel almost obvious now because we have lived with it for generations, but it was a major break from older pictures of an eternal static cosmos. Even Einstein, when first applying general relativity to the universe as a whole, had preferred a static model and introduced an additional term into his equations to hold the universe steady. Later, when expansion became harder to deny, that early preference looked less secure. Whether or not one repeats the famous story about his greatest blunder, the broader point stands. Theoretical instinct had leaned one way. Observation pushed the other way. Nature had its own opinion. And this is where Hubble's discovery becomes especially relevant to our present topic. The recession of galaxies was not merely a collection of high speeds to be plugged into a chart. It forced astronomers and physicists to ask what kind of recession this was. Were galaxies simply hurled outward through pre-existing space? Or was the universe itself expanding in the geometric sense suggested by solutions to general relativity? Once that question was asked seriously, the modern picture began to take shape. The observed drift of galaxies was not best thought of as debris from an explosion into emptiness. It was better described as the large-scale expansion of space. The quietness of that drift is important too. Galaxies are not usually racing across the sky in a dramatic visual sense. We do not watch them slide past one another as one ship passes another at sea. Their recession is inferred from redshift and distance. The universe changes on scales so large and over time so long that the effect is hidden inside data long before it is ever visible to the eye. That can make cosmology feel almost unreal at first, as though it is too far removed from human experience to count as direct knowledge. But the opposite is true. These measurements are exactly how science extends beyond unaided perception. The universe is not obliged to display its structure at human speed. There is also a subtle lesson in the fact that Hubble himself was cautious. He measured the relation, he described the apparent recession, but the deeper interpretation, whether the redshifts should be understood as velocities in a simple sense or as part of a more general expanding spacetime picture, was tied up with theory as well as observation. That caution is easy to miss when later generations compress the story into one neat line about Hubble discovering the expanding universe. In truth, the observational relation and the theoretical framework matured together. The data told astronomers something profound was happening. General relativity provided a language in which that something could be understood as cosmic expansion. That partnership between observation and theory is one of the best features of science when it is working well. Observation alone can reveal a pattern, but theory helps explain what sort of pattern it is. Theory alone can produce elegant possibilities, but observation decides whether nature actually uses them. Hubble's discovery sits right at that junction. The data showed a lawful relation between distance and redshift. Relativistic cosmology offered a universe in which large-scale expansion made sense. The two met, and modern cosmology became much harder to ignore. It also became much larger in its implications. Once astronomers accepted that the universe is expanding, they could begin to estimate expansion rates, ages, sizes, and past conditions. Early estimates were rough and often wrong by large factors, in part because distance measurements are notoriously difficult, and because the cosmic distance ladder had many rungs still being refined. But the direction of the result mattered more than the first numerical details. The universe was dynamic. That conclusion survived every later improvement in instrumentation and method. Better telescopes, better detectors, better calibration, better standard candles, better understanding of galaxy properties. All of it sharpened the picture, but none of it restored a static cosmos. If anything, later work deepened the strangeness. The expansion was not only real, it became a framework within which other discoveries made sense. The cosmic microwave background fit naturally with a hot, dense early universe. The abundance of light elements fit the same picture. Large-scale structure formation fit a universe evolving over time. Much later, the discovery that the expansion is accelerating would add another layer of surprise. But the foundation remained the relation Hubble helped bring into focus. Distant galaxies are not arranged in a fixed cosmic museum. They are participants in an evolving universe. There is a practical reason this matters for the question of faster-than-light expansion. Hubble's relation makes it clear that recession grows with distance. That means if the universe is large enough, and the relation holds on sufficiently large scales, then there will be distances at which the recession rate exceeds the speed of light. This is not an extra bonus feature added later to upset people who are just becoming comfortable with redshift. It is built into the logic of the expansion itself. Once recession increases with distance, and once enough distance is available, superluminal recession becomes unavoidable. Not because galaxies acquire magical engines, not because relativity has stopped caring, simply because more expanding space lies in between. Seen this way, the faster-than-light issue is not some embarrassing corner case. It is a natural consequence of the very pattern Hubble helped establish. The farther away a galaxy is, the greater the recession. Keep going far enough, and the recession exceeds light speed. The observational story therefore does not merely support expansion in a general way, it prepares us for exactly the conceptual distinction we have been building. Local motion remains constrained by relativity. Global recession produced by expanding space can behave differently. Another thing worth noticing is how ordinary the observational ingredients seem compared with the scale of the conclusion. A star that flickers in a regular pattern, a spectrum shifted toward red, a telescope mirror collecting faint light on a mountain. These are modest tools in one sense, There is no single instrument labelled universe expander. Yet from those ingredients, astronomers learned that the cosmos itself changes in time. This is one of the quiet strengths of astronomy. It works with light, patience, and inference, and from them it reconstructs histories measured not in years or centuries, but in billions of years. That kind of inference can seem almost too indirect until one remembers how often science proceeds this way. We do not see atoms with the naked eye, yet atomic theory is secure. We do not see tectonic plates drifting in one glance, yet geology is secure. We do not feel Earth orbiting the Sun, yet heliocentrism is secure. The test is not whether a phenomenon flatters human senses. The test is whether different lines of evidence converge on one coherent picture. In the case of cosmic expansion, they do. So Hubble's discovery was not just about galaxies moving away. It was about recognizing a lawful pattern in the large-scale universe and taking seriously what that pattern implied. The Milky Way was not the whole universe. The spirals were galaxies. Their light was shifted. Their distances could be measured. Their recession increased with distance. The universe was not static. The sky contained history. Space on the larger scales was doing something our everyday intuition had never prepared us for. And once that much is accepted, the next question becomes harder to avoid. If the observations really do point to a universe whose large-scale distances grow over time, then we have to ask how that can happen without breaking the relativistic limit we have spent so much care preserving. In other words, what exactly is the rule book here, and how does expanding space manage to follow it even when the recession between distant galaxies becomes faster than light? The key to this is that Einstein was never actually trying to forbid the universe from changing. He was not writing a set of rules designed to keep space neat and still like a perfectly ironed tablecloth. What he gave us was a way of understanding how space, time, matter, energy, motion and gravity all fit together. And once you look carefully at what his theory really says, the puzzle begins to soften. Space can stretch. Distances can grow. Galaxies can recede from one another at rates greater than light. And none of that requires Einstein to be quietly removed from the story in embarrassment. In fact, it is his own framework that allows it. The trouble begins with the shortened version of the rule. Nothing can go faster than light. We hear that sentence so often that it starts to feel like a universal ban on anything that looks rapid, dramatic, or scientifically suspicious. But what relativity actually says is more specific and more interesting. No object with mass can move through its local region of space faster than light. No signal can locally outrun light. No physical influence can hop ahead of the causal structure built into space-time. That is the real heart of the matter. The rule is about local motion, local measurements, and local causality. That word local is not a technical nuisance, it is the whole point. In physics, especially in relativity, local means what can be measured in a small enough region of space-time that the effects of curvature can be ignored and the familiar laws take their simplest form. In that local neighbourhood, space-time behaves as special relativity says it should. Light has its usual speed. Massive objects move more slowly, cause stays ahead of effect in the proper order. No rocket, no particle, no ambitious civilization with an unhealthy appetite for shortcuts gets to violate that structure. But the universe as a whole is not one giant local neighbourhood. That is where many people slip without noticing. They hear a statement about nearby physics and stretch it across the entire cosmos, as though the universe were one flat static stage where all distances can be compared in a single simple way. General relativity does not describe the cosmos like that. It allows space-time to curve, evolve, expand, and respond to matter and energy. So when we speak about the recession of distant galaxies in an expanding universe, we're no longer speaking about one object blasting past another inside a single shared local frame. We're speaking about the geometry of space-time itself changing over immense distances. That distinction is what keeps Einstein safe from contradiction. If a galaxy far away is receding from us because the space between us is expanding, then that galaxy is not locally doing anything forbidden. In its own neighbourhood, light still behaves normally. Nearby observers there still measure the usual speed of the light. Spaceships there still cannot locally surpass it. If you were somehow standing in that galaxy with a clipboard and a very good watch, the laws of relativity would not appear broken in the least. The same is true here. Locally everything is in order. The oddness only appears when we compare two remote regions across a universe whose geometry is evolving. One way to make this feel more concrete is to imagine a very long line of observers spread through an expanding cosmos, each one close enough to the next that they can compare measurements in an ordinary local way. Every observer finds that light passing by them moves at the expected speed. Every observer finds that local objects obey relativity. There is no point along the line where a law suddenly gives up and says, "I cannot be bothered with this anymore." Yet when you step back and compare the total distance between the observers at one end and the observers at the other, that total distance can grow faster than light if the line is long enough and the expansion is strong enough. The local laws remain untouched. The large-scale separation changes because the geometry across the whole line changes. There is something quietly elegant about that. It means the universe does not need exceptions. It does not need hidden escape clauses. The apparent conflict comes from asking one sentence to do work it was never meant to do. Nothing moves through local space faster than light. Fine, but the distance between faraway regions of an evolving universe is not the same thing as a local speed through static space. Once that is clear, the scandal disappears. It may help to think about how general relativity differs in spirit from the older Newtonian picture. In the older picture, space and time form a kind of passive background. Matter moves around, forces act, but the stage itself stays put. General relativity changes that. The stage becomes part of the play. Matter and energy shape space-time. Space-time tells matter how to move. The geometry is active. It is not a blank box. So if the universe is filled on large scales with matter and radiation, and whatever else contributes to its overall behaviour, then the global geometry can evolve. One possible evolution is expansion. Not objects flying into an empty external room, but the metric structure of space changing with time. That word metric is useful here even if it sounds a little formal. It simply refers to the rule by which distances are measured. In an expanding universe, the metric changes in such a way that the proper distance between widely separated comoving galaxies increases over time. That is a long way of saying the universe has a built-in scale that grows. Once you know that, faster-than-light recession is no longer mysterious. If the scale factor grows, and enough distance is involved, then the rate at which total distance increases can exceed the speed of light. The galaxies themselves have not burst through a local barrier. The measuring stick that defines the large-scale distance has changed. This is why cosmologists can say, without wincing, that some galaxies recede faster than light. They are not saying those galaxies are locally racing through their neighbourhoods in a rebellious mood. They are saying that when one uses the proper description of an expanding universe, the distance between us and sufficiently distant galaxies grows at a rate greater than light. That rate is a property of the expanding geometry, not of forbidden local motion. Now, this raises a very natural question. If the rule is about local motion, why do we care so much about local measurements in the first place? Why not simply declare that anything the universe does globally must also be allowed for individual objects? The answer is causality. Local light speed is not just a number. It is the speed at which causal influence propagates in vacuum. It marks the boundary of who can affect whom and when. If local faster-than-light signalling were allowed, one could create situations in which effects precede causes in some frames of reference. Relativity would no longer provide a stable order of physical explanation. That is why Einstein's rule is strict where it applies. But global expansion does not produce that sort of local causal mischief. No galaxy sends a local signal through its nearby space faster than light. No spacecraft overtakes a light beam beside it. No message is delivered to a nearby observer before it was sent. The large-scale separation of galaxies can grow superluminally without allowing local causal paradoxes. The geometry changes, but the local causal structure remains intact. That is the crucial harmony. Expansion does not tear causality apart. It leaves the local light cones, if I may borrow that image for a moment, behaving exactly as relativity requires in each neighbourhood. It is rather like the difference between a law governing how fast a person may run across a field and a change in the size of the field itself. The person can obey the running limit perfectly while the field stretches beneath the landscape surveyor's feet. The total distance from one fence to the other can increase faster than any runner could cross it, but that tells you nothing about the runner breaking the speed rule. The change lies in the background geometry, not in the local motion. Of course, no analogy survives too much enthusiasm. The universe is not a literal field, and space-time is not a patch of rubber in the everyday sense. But the contrast remains useful. Einstein's limit governs local travel through space-time. It does not forbid space-time itself from having a dynamic large-scale structure in which distant separations grow rapidly. There is another point worth sitting with for a moment because it often feels surprising even to people who already know the basic answer. General relativity itself predicts non-static universes quite naturally. If you take the equations seriously and apply them to a universe that is homogeneous and isotropic on large scales, meaning roughly the same everywhere and in every direction, then expansion or contraction follows very naturally. A perfectly static cosmos is actually the more delicate arrangement. That is part of why the story of Einstein introducing an extra ingredient to hold the universe still has remained so memorable. The mathematics itself was already comfortable with a changing cosmos. It was human instinct that preferred stillness. And this is deeply relevant to our question, because it means the expanding universe is not an embarrassing side effect tacked onto relativity. It is one of the natural behaviours relativity permits. Once the universe expands, distance-dependent recession follows. Once distance-dependent recession follows, sufficiently large separations can exceed light speed. So the very theory that gives us the local speed limit is also the theory that gives us the framework in which large-scale superluminal recession makes sense. There is no civil war within the equations. The conflict exists only in a simplified slogan. One of the best ways to feel this more clearly is to remember that velocities in curved space-time are not always globally comparable in the way everyday intuition assumes. If two objects are right next to each other, you can compare their velocities cleanly. If they are on opposite sides of an evolving universe, things get trickier. There is no single universal inertial frame covering the whole expanding cosmos in a simple way. That means statements about the recession speed of very distant galaxies are not the same kind of statements as measuring how fast one nearby spacecraft passes another. The mathematical and physical context is different. This is why trying to imagine a very distant galaxy as though it were just a fast-moving object in ordinary empty space leads to trouble. It imports the wrong kind of velocity into the wrong situation. The recession is not a local velocity through a shared static background. It is a rate of increase of proper distance in a cosmological space-time. That may sound like a technical distinction, but it is the reason the whole subject makes sense. There is also a common emotional reaction to all this, which is to suspect that physicists are merely hiding behind careful wording. Space is expanding faster than light, you say. Then when challenged, you retreat into local versus global language. Fair enough. It can sound evasive if one has not yet seen why the distinction matters, but this is not a lawyerly trick. Physics often depends on exactly these differences. Temperature is not the same as heat. Weight is not the same as mass. Speed through a local inertial frame is not the same as recession due to cosmological expansion. Precision is not a way of dodging the question. It is the way of answering it honestly. And there is observational support for taking the distinction seriously. Distant galaxies are redshifted in a manner consistent with expansion. The cosmic microwave background supports a hot, dense early universe. The large-scale distribution of galaxies fits an evolving cosmic metric. The success of the standard cosmological model is not based on one verbal maneuver. It rests on a network of evidence that works because general relativity treats space-time as dynamic. If one insisted that all recession must be ordinary motion through static space, the whole explanatory structure would become strained and incomplete. Still, let us stay close to the core idea. How can space stretch without breaking Einstein's rules? Because Einstein's rules are local rules about motion, signals and causality in space-time, and general relativity allows space-time itself to evolve on large scales. Expansion changes the distance between remote galaxies without requiring either galaxy to locally outrun light. Every local observer continues to find the usual laws intact. Every light beam still locally does what light beams do. What changes is the large-scale metric of the universe. This also explains why the phrase faster than light expansion should not make us imagine cosmic panic. It does not mean that a nearby galaxy might suddenly vanish from your telescope because it has switched into an illegal speed mode. It does not mean light has become obsolete. It does not mean the universe has found a loophole so obvious that every science fiction writer ought to have retired by now. It means that on sufficiently large scales, the amount of space between regions can grow at a rate that exceeds light speed, while locally all the usual relativistic structure remains in place. Once you accept that, several other pieces begin to fall into place. You can see why there are horizons in cosmology. You can understand why some galaxies are in principle unreachable. You can understand why the early universe could undergo a brief period of astonishingly rapid expansion without every local law collapsing into nonsense, and you can begin to see why light itself, despite always behaving properly in each local region, can still struggle against a globally expanding geometry over very long journeys. There is something reassuring in the consistency of it. The universe is not patched together from contradictory rules. It is stranger than common sense expects, but it is not sloppier. The same theory that tells us no local object with mass outruns light also tells us that space-time can curve and expand. The same framework that protects causality locally also permits distant galaxies to recede superluminally in a cosmological sense. It is one picture, not two competing ones. And that unified picture matters even more when we turn to one of the most dramatic episodes in cosmic history, because the present expansion of the universe is only part of the story. In the earliest fraction of cosmic time, according to our best models, the universe went through a phase of expansion far more violent than the gentle drift Hubble helped reveal. Space did not merely expand, it expanded with extraordinary speed, smoothing and stretching the young universe in a way that still shapes what we observe today. If the ordinary expansion already sounds bold, the early universe pushes the idea to an even more astonishing extreme, and yet it still does so within the same broad relativistic framework. The idea of expansion becomes even more striking when we carry it backward into the earliest history of the universe, because the slow, large-scale drift of galaxies that Hubble helped reveal appears to be only the calm after a much more dramatic opening act. According to the modern inflationary picture, the young universe went through an extremely brief period of accelerated expansion very early on. During that interval, space did not merely get a little larger, it expanded by an enormous factor in a tiny fraction of a second. NASA describes this as a period when the universe expanded faster than the speed of light for a fraction of a second, while the European Space Agency explains that this early burst may have lasted only until roughly a tiny fraction of a second after the beginning and increased the size of the universe by an enormous factor. At first glance, inflation sounds like the ultimate violation of everything we have been carefully trying to protect. If ordinary, faster-than-light motion is forbidden, then surely a phase of even more rapid expansion should set every alarm bell ringing. But this is exactly where the distinction between motion and expansion proves its value. Inflation is not a story about matter or signals blasting through local space in defiance of relativity. It is a story about space itself expanding at a wild rate. NASA is very direct on this point. The rapid growth of inflation may sound as though it violates relativity, but the expansion is of space only, with no matter or information carried between points at faster than the speed of light. That is why inflation belongs inside the same broad relativistic framework we have already been discussing rather than outside it. The reason cosmologists became interested in inflation in the first place was not because they wanted to make the early universe more theatrical. The standard hot Big Bang picture was already powerful and successful, but when physicists looked closely at it, a few puzzles remained stubbornly awkward. One of them was the flatness problem. On the largest scales, the universe appears remarkably close to geometrically flat. NASA and ESA both note that inflation helps explain this apparent lack of curvature on cosmic scales. Without some early mechanism to stretch the geometry smooth, that large-scale flatness looks like a finely balanced initial condition that seems uncomfortably special. Inflation offers a way out by rapidly expanding any initial curvature until the observable universe looks extremely flat, much as a small patch on a very large sphere can appear flat to any local observer. Another puzzle was the horizon problem, which is one of those names that sounds technical until you realize it points to a very plain difficulty. Different regions of the cosmic microwave background are widely separated on the sky, yet they have nearly the same temperature. In an ordinary non-inflationary Big Bang picture, many of those regions would never have had enough time to exchange light or other signals before the microwave background was released. So why do they look so similar? NASA describes inflation as a solution by proposing that a small parcel of space expanded rapidly, allowing regions that were once close enough to interact to become enormously separated later on. In other words, the smoothness we observe across the sky may reflect the fact that those regions were once neighbours before inflation pulled them far apart. There is something satisfying about that, because it turns a mystery of coordination into a mystery of history. Instead of asking how far flung parts of the universe managed to agree with one another, despite never meeting, inflation says they may well have met in the very early universe when everything was compressed into a much smaller region. The later vast separations did not erase that earlier contact, they only hid it from direct view. It is a neat example of how cosmology often solves a puzzle, not by changing the present, but by changing our picture of the past. The early universe was not just smaller. Under inflation, it was also arranged in a way that lets the later large-scale uniformity make sense. Inflation also does something else that may be even more important for the universe we actually see around us. It does not leave the cosmos perfectly smooth. Instead, it takes tiny fluctuations and stretches them to cosmic scales. The European Space Agency notes that the period before the formation of the cosmic microwave background plays a key role in determining the tiny fluctuations we observe in that background today. Modern inflationary theory proposes that very small quantum fluctuations in the early universe were enlarged during inflation, and later became the seeds from which galaxies and larger cosmic structure grew. That idea gives inflation a remarkable double role. It explains why the universe is smooth on large scales, while also explaining why it is not completely smooth. We need both. A universe with no structure would contain no galaxies, no stars, no planets, and no one sitting awake wondering about any of this. That combination of smoothing and seeding is one of the reasons inflation has held on so strongly in cosmology. It does not merely patch one hole, it helps tie several observations together at once. The universe looks flat. Inflation can explain that. The microwave background looks similar across vast distances. Inflation can explain that too. The universe contains tiny primordial irregularities that later grew into structure. Inflation offers an origin story for those as well. That does not mean every detail is settled, or every version of inflation is equally good. It means the broad idea has explanatory power that is hard to ignore. Now, because the word inflation sounds like the universe puffing up like a balloon, it is easy to imagine an ordinary explosive event. But inflation is stranger than an explosion. In an explosion, matter rushes outward through surrounding space. In inflation, the expansion is in the geometry of space itself. Every region participates. There is no central launch point from which material is shot into an external void. The distances between regions increase because space-time evolves. This is why inflation fits so naturally with the lesson we have already been building. It is the expansion of space taken to a more extreme early universe setting, not a special exception to the usual rules. What then caused inflation? Here the script becomes more cautious, because inflation is a well-motivated framework, but the detailed physics behind it is still not known with certainty. NASA states plainly that scientists are not sure what powered inflation or what came before it. One common family of ideas involves a field with an energy density that acts somewhat like an almost constant vacuum energy for a brief time, driving rapid expansion until that phase ends and the universe settles into the hotter, more familiar Big Bang evolution. But while such models can be written down and compared with observations, we do not yet have direct laboratory confirmation of the specific mechanism. This is a good place to keep our confidence and our humility in the same room. The broad picture is influential and successful, but the engine under the hood is still a topic of active theoretical work. Even the duration of inflation, when described in ordinary words, has a slightly comic quality, because human language was not built for time intervals this short. The European Space Agency describes the inflationary phase as lasting only until roughly 10 to the minus 32nd seconds after the beginning, which in ordinary speech means unimaginably early and unimaginably brief. The point is not to memorize the number like a password. The point is to recognize that inflation, if it occurred, belongs to the first tiny sliver of cosmic history, long before atoms, long before stars, long before the cosmic microwave background itself was released. By the time that background light began its long journey, inflation was already ancient history in cosmic terms, though its fingerprints were still present in the conditions of the young universe. There is a good practical reason cosmologists care so much about those fingerprints. We cannot travel back to the inflationary era. We cannot bottle a piece of it and bring it into a laboratory. What we can do is examine the sky for the patterns inflation should leave behind. The microwave background is especially important here because it is ancient light, released about 375,000 years after inflation according to NASA's WMAP overview, and it carries subtle information about earlier conditions. Tiny temperature variations across that background act like a fossil record of the early universe. They do not show inflation directly in the way a camera would show a thunderstorm, but they preserve clues about the primordial fluctuations inflation is supposed to have stretched across the cosmos. This is where missions like WMAP and Planck became so important. Their measurements of the cosmic microwave background mapped those tiny variations with extraordinary precision, turning the sky into a detailed test of cosmological models. The Planck collaboration has reported that its inflation constraints are consistent with earlier releases while improving the uncertainties, and ESA emphasizes that the nature and distribution of the tiny seeds visible in the background help determine the composition and evolution of the universe from its birth onward. In effect, inflation is not accepted because it sounds grand. It is judged against data. If it had predicted the wrong kind of fluctuations, the wrong spectrum of irregularities, or a universe wildly unlike the one observed, cosmologists would have had every reason to move on. That said, inflation is not one single model, with one single exact prediction. It is more like a family of related ideas. Some versions fit current observations better than others. Some predict different patterns of primordial fluctuations. Some are now constrained or disfavored by the data. This is where the subject becomes more technical than we need for the present discussion, but the broad lesson is worth keeping. Observations have not simply stamped every inflationary proposal approved. They have narrowed the field. The Planck collaboration's work on constraints on inflation is very much about that process of sorting viable models from less viable ones. The picture remains active, tested, and refined rather than frozen into dogma. One of the most discussed possible signatures of inflation is primordial gravitational waves. If inflation occurred, many models suggest it could have generated gravitational ripples in the early universe, and those ripples might have left a special pattern in the polarization of the cosmic microwave background. This possibility has excited astronomers for years, because it would offer a much more direct glimpse into the inflationary era. But here again, the story is one of careful restraint. NASA's Jet Propulsion Laboratory has noted that gravitational waves from the early universe remain elusive. There have been moments of excitement and moments of correction, which is very much how science behaves when the signal is hard and the stakes are high. So inflation is strongly motivated and supported indirectly by several lines of evidence, but some of its most dramatic hoped-for signatures remain unconfirmed. There is something healthy about that uncertainty. It keeps the subject honest. It reminds us that cosmology, for all its sweeping scope, is still an empirical science. Inflation may be the leading explanation for several major features of the universe, but cosmologists still want better evidence, tighter constraints, and clearer links between the broad scenario and the underlying particle physics. That is not weakness. That is science behaving properly. A successful idea is not one that people merely repeat. It is one they keep trying to break and fail to break. Still, even at the broad conceptual level, inflation has an extraordinary consequence for the question we began with. It shows that faster-than-light expansion is not just a late-time curiosity involving distant galaxies. It may have been a defining feature of the early universe itself. NASA's overview says the universe expanded faster than the speed of light for a fraction of a second during inflation. But this did not mean particles were locally outracing photons in some grand cosmic sprint. It meant space-time itself expanded at such a rate that regions were driven apart with enormous speed. The same distinction that protects Einstein's local speed limit in the present universe protects it during inflation as well. The scale of the expansion changes, the local causal rules remain, and there is an almost funny contrast in that. The modern universe expands in a patient, measured way. Distant galaxies drift apart, and over billions of years the structure changes. Inflation, by contrast, is the early universe in a hurry. The cosmos does not stroll, it bolts. Not because it has somewhere urgent to be, but because the physics of that early state appears to allow a brief period of extraordinary accelerated expansion. Afterward, the universe transitions into the hot expanding state from which ordinary Big Bang evolution proceeds. In that sense, inflation is not the whole story of cosmic expansion. It is an opening surge that sets the stage for much of what follows. If you take a step back, the appeal of inflation becomes clearer. It offers a universe that starts from conditions capable of producing the one we see. It gives a reason for large-scale flatness. It gives a reason for the near uniformity of the microwave background. It gives a mechanism for stretching microscopic irregularities into macroscopic seeds of structure. And it does all this using the same broad lesson we have been circling from the start, namely that the geometry of space is not passive. It can evolve dramatically. It can shape what later becomes possible. The galaxies, clusters, and long dark stretches between them may all owe something to that early brief episode when space expanded with astonishing speed. There is also a more human reaction to inflation, and perhaps it is worth admitting. It can sound almost too extravagant to be true. The universe, in its first tiny instant, expands faster than light, smooths itself out, preserves tiny quantum fluctuations, and plants the seeds for everything that follows. It sounds like the kind of idea one would reject in a first draft for being too convenient. Yet the reason physicists take it seriously is not because it is dramatic. It is because the observations we do have keep nudging us back towards something like it. Not necessarily every model, not necessarily every detail, but something in that family of early accelerated expansion continues to do impressive, explanatory work. And once inflation has entered the story, another consequence follows naturally. If the universe underwent such rapid early expansion, then not everything that exists now was always in view of everything else, and not every region of the cosmos is accessible to us even in principle. Expansion does more than spread matter apart. It creates limits on observation, it stretches light, it shapes what can ever be seen and what will remain forever beyond the reach of our telescopes. That is where the story moves next, because once space is allowed to grow this way, we are forced to confront a quieter but equally strange idea. The universe has horizons, and some of them are not unlike a permanent boundary on what any observer can know. When people first hear the phrase observable universe, it often sounds as though the universe must have an edge somewhere, like the rim of a dark bowl or the far wall of a gigantic room. That image is understandable, but it points in the wrong direction. The observable universe is not the whole universe ending at a boundary. It is the portion from which light has had time to reach us since cosmic history began. NASA explains the basic logic in exactly that way. We can only see out to the distance from which light has had enough time to arrive, and because the universe has expanded while that light was travelling, the observable universe is far larger than a simple multiplication of the universe's age by the speed of light would suggest. NASA's educational overview gives the modern picture as roughly 47 billion light-years to the most distant currently observable regions, or about 94 billion light-years across. That already tells us something important about horizons in cosmology. A horizon is not always a wall. Sometimes it is a limit set by history. If light needs time to travel, then looking far away means looking back in time. NASA's Hubble overview puts it plainly. Light takes time to reach us, which means the more distant an object is, the older the version of it we are seeing today. A nearby star may be shown to us as it was a few years ago. A distant galaxy may appear as it was billions of years ago. In that sense, every telescope is a machine for delayed news. The sky does not show us the universe all at once. It shows us layer after layer of the past, with deeper layers requiring longer journeys of light. This is where redshift becomes more than a technical term. It becomes part of the way the universe hides and reveals its own history. NASA's Hubble description of cosmological redshift says that light from galaxies stretches to increasingly longer and redder wavelengths as it travels through an ever-expanding universe. ESA says much the same thing in simpler words. The wavelength is stretched, so the light is shifted toward the red. For very distant objects, this is not just a decorative colour change. It moves light out of the visible part of the spectrum and into the infrared, which is one reason telescopes like Webb were built to look in wavelengths our eyes cannot see. The farther the light has travelled through expanding space, the more it has been stretched on the way to us. There is something almost gentle about that process. The universe does not simply place old galaxies far away and leave them there. It stretches their light as it sends it on its journey. By the time that light reaches our instruments, it carries two messages at once. It tells us something about the source that emitted it, and it tells us something about the expansion of the space it crossed. NASA's Webb Early Universe Explainer notes that for the first stars and galaxies, light that began as visible or ultraviolet radiation reaches us shifted into the near and mid-infrared. So when astronomers point an infrared telescope toward the deeper sky, they are not using a clever gimmick. They are adapting themselves to the actual behaviour of light in an expanding universe. Now, if light travel lets us keep pushing farther back, it is natural to ask whether we can simply continue until we see the beginning itself. This is where the universe introduces a more severe horizon. NASA explains that the cosmic microwave background is the oldest light we can observe. That radiation was released when the young universe became transparent after the first atoms formed, roughly 380,000 years after the beginning. Before that, the early universe was opaque. Light could not travel freely for long because it kept scattering off free electrons. In other words, there is a fog bank in cosmic history. We cannot see through it with ordinary light because ordinary light could not yet travel cleanly through that early plasma. The microwave background is therefore not just old light, it is the first light that could move freely across the cosmos and keep going until some tiny fraction of it reached us. That is one of the reasons the microwave background feels so special in cosmology. It is not merely ancient, it marks a limit. Beyond it, in terms of ordinary electromagnetic observation, the universe becomes hidden from direct view. We can still study earlier times indirectly through theory, through particle physics, through the distribution of primordial fluctuations, perhaps one day through gravitational waves, but with light itself there is a practical stopping point. The universe only became transparent after those first atoms formed. NASA's summary of cosmic history calls the microwave background the oldest light we can observe, and ESA's Planck material likewise describes it as the most ancient light observed in the history of the universe. So even though telescopes can take us astonishingly far back, they eventually reach a surface beyond which visible history becomes inaccessible to direct imaging. It is also worth noticing that the observable limit is not the same as the age of the universe translated into distance in the most naive way. This is one of the first things that surprises people, and it is a very useful surprise. If the universe is about 13.8 billion years old, it is tempting to think that the farthest visible objects must be about 13.8 billion light-years away. But NASA's educational material explains why that is not the right picture. While the light was travelling, the universe itself was expanding, so the distant matter that emitted that light is now much farther away than the simple light travel time would suggest. That is why the observable universe can be about 94 billion light-years across, even though the universe is much younger than 94 billion years. The journey took billions of years, but the destination did not stand still while the signal was in transit. This is one of those moments where the difference between ordinary intuition and cosmological reality becomes impossible to ignore. In an ordinary city, if someone a mile away sends you a signal, you can assume they remain roughly a mile away while the signal travels. On cosmic scales, that assumption fails. The source and the observer are embedded in an expanding geometry. Light still does what light does in each local region, but the large-scale distance between emitter and receiver evolves throughout the journey. So when astronomers say the early universe is visible at incredible distances, they are talking about a history written into redshift, light travel time, and expansion all at once. A single number never quite captures the whole story. Horizons also have a more personal quality than we sometimes admit. The observable universe is centered on the observer, not because we are cosmically special, but because every observer can only see as far as light has had time to reach them. A galaxy far away has its own observable universe centered on itself. It too sees an ancient sky and a finite horizon. It too would describe the oldest observable light as coming from its own cosmic microwave background sky. This is a lovely example of the universe refusing to flatter anyone in particular. Every observer gets a horizon, not because they are privileged, but because causality and light travel time impose the same broad limitation everywhere. That is one reason cosmological horizons feel both intimate and impersonal. They belong to us, but they do not belong to us alone. Redshift deepens that feeling because it means that remoteness is not just about distance, it is also about transformation. When NASA discusses the early universe and the purpose of Webb, it emphasizes that the first galaxies are not merely faint because they are far away. Their light arrives shifted to longer wavelengths. The early universe therefore has to be sought in infrared light, not because infrared is somehow more magical, but because the expansion of space has moved the evidence there. Very distant galaxies are not simply small points in the dark. They are ancient signals changed by the journey itself. We do not observe them in spite of the expanding universe. We observe them through the signature that expansion leaves behind. There is another edge to what we can see, and this one is tied not to the past fog of the young universe, but to the long-term behaviour of expansion. NASA's dark energy overview says the expansion of the universe, after slowing for a long while, began accelerating about 9 billion years after the beginning, and is now speeding up under the influence of what scientists call dark energy. That means the large-scale universe is not merely expanding, it is expanding in a way that increasingly separates distant regions from one another. Even without introducing more formal language, the consequence is clear enough. The future does not necessarily give us access to everything we cannot see today. Some regions are so remote and the expansion is so persistent that their light cannot simply be expected to wander into view later on. In an accelerating universe, horizons are not only about how long we have waited, they're also about how the stage itself keeps changing while we wait. That has a quietly sobering implication. It means that the phrase "what we can ever see" is not just poetic, it is physical. There are limits set by the age of the universe, by the early opacity of the cosmos, and by the ongoing expansion of space. We can see only as far back as the oldest freely travelling light allows. We can see only as far out as light has had a chance to reach us through an expanding universe. And because the expansion is accelerating, the far future is not simply a bigger and better observatory from which all remaining mysteries will finally be exposed. Some of the universe is not hidden merely by current technological weakness. It is hidden by causal structure. That does not make cosmology bleak. In some ways, it makes it more interesting. The universe is not just big, it is selective about what can be known from any one place. It hands us a finite sphere of evidence and asks us to infer the larger picture from what arrives inside it. That is why the microwave background matters so much. That is why redshift matters so much. That is why precise distance measurements matter so much. We are reconstructing a reality that is larger than our horizon from the signals that manage to cross it. Every observation is a crossing. Every galaxy image is a successful arrival from some more distant time and place. There is also something rather beautiful about the fact that our deepest views are always oldest. In everyday life, seeing more clearly usually means seeing what is here now. In cosmology, seeing more deeply means seeing what was there then. The farther we reach, the younger the universe becomes. NASA describes Hubble as a time machine for exactly this reason, and Webb extends that time travel farther into the infrared realm, where the first galaxies can still be found. So the edge of the observable universe is not simply a far-off shell in space. It is also an archive of earlier and earlier epochs, ending for light-based astronomy at the glow of the microwave background. If all of this sounds a bit unsettling, I think that is part of the point. Horizons remind us that the universe is not laid out for us all at once. Redshift reminds us that light is altered by the cosmic journey. The microwave background reminds us that even light has a beginning point for free travel. And the accelerating expansion reminds us that the future is not guaranteed to open every locked door. Yet there is comfort in the coherence of it. The same expansion that explains redshift also explains why the observable universe is larger than a simple light travel estimate. The same early universe physics that made the cosmos opaque also explains why the microwave background is the oldest light we can see. The same late-time acceleration that drives galaxies apart also shapes the ultimate limits of observation. The story is strange, but it holds together. And once you start to see the universe in those terms, another misunderstanding begins to fade. Faster-than-light expansion stops sounding like a license for faster-than-light travel. Horizons make that especially clear. Space can stretch in such a way that very distant galaxies recede from us faster than light. And still, that does not mean a ship can simply ride the expansion to overtake causality or ignore the local rules of relativity. In fact, the existence of cosmological horizons points in the opposite direction. The structure of expansion limits access. It does not casually grant it. So the next step is to turn from what we can see to what we can do, and to ask why the universe's ability to expand faster than light does not hand us an equally convenient way to travel faster than light ourselves. That limitation is really the first clue, because a universe with horizons is not offering us a shortcut. It is telling us, very calmly, that expansion can separate places more effectively than any traveller can bridge them. In relativity, the speed of light sets the local limit for motion, information, and influence, and Einstein online is explicit that in general relativity this limit is defined locally, in the sense that no object or influence can overtake a light signal in a side-by-side comparison. The same source also explains that light propagation defines the causal structure of space-time, which is just a more formal way of saying that the order of cause and effect is built around what light can and cannot connect. So when people hear that the universe expands faster than light, and immediately imagine an invitation to super-fast travel, they're quietly swapping one category for another. Expansion changes the distance between remote regions. Travel still means moving a ship, a signal, or a person through one local region after another, and in each of those regions the usual relativistic limit remains in force. That is the heart of the answer. Faster than light expansion is not faster than light transportation. It is not a vehicle, it is not a free launch system, it is not a cosmic conveyor belt waiting for ambitious civilizations to step aboard with luggage and snacks. The reason is simple once it is said plainly. The expansion of the universe is not a local wind blowing things outward in a chosen direction. It is a large-scale change in the distances between faraway regions of space-time. Einstein online describes the expanding universe in exactly those terms, saying that the distance between faraway regions of space steadily increases with time. That statement is about geometry, not propulsion. If two galaxies become more distant because space between them grows, nothing about that process tells you how to make a spacecraft in one galaxy cross the local space around it faster than light. The ship would still have to travel through its nearby space-time lawfully, and lawful travel remains sublight. Expansion can make the map larger. It does not give the traveller illegal shoes. There is also a more practical problem. Cosmic expansion is not even very useful where travel begins. On small scales, the universe does not expand in the way the popular picture sometimes suggests. Local systems that are gravitationally bound do not simply drift apart because the cosmos is getting larger overall. NASA notes that galaxies in close proximity can still collide because they are bound by gravity, despite the expansion and acceleration of the universe, and the Milky Way and Andromeda are the classic nearby example of that local rule beating the global trend. NASA also describes galaxies as huge systems whose stars are bound together by mutual gravity. That means your solar system is not expanding with the Hubble flow, your galaxy is not being stretched into cosmic toffee, and a spacecraft leaving Earth does not begin its journey on a patch of space that is conveniently swelling in the desired direction. Local gravity, local binding, and local dynamics dominate where any actual mission would start. So even before we ask whether expansion could make travel easier, the answer is already leaning no, because the form of expansion that matters cosmologically is not something you can simply harness in your neighbourhood, like a favourable current. And even if one imagines a journey between galaxies rather than between planets, the situation still does not improve in the way science fiction often hopes. A ship heading toward a distant target must pass through one local region of space-time after another. In each local region, relativity still applies exactly as before. Einstein online states that in both special and general relativity, the speed of light sets the upper limit for the transmission of signals and influences, and that no object, matter, or information can directly overtake or catch up with light locally. So a traveller cannot simply point to a galaxy that is receding faster than light and say, "Excellent, I shall use that same mechanism." The galaxy is not locally outracing light through the space around it. The total distance is increasing because of expansion across a vast scale. A ship, by contrast, would need to cross those local stretches one by one. The distinction is like the difference between a destination being carried away by the stretching of the landscape and a runner actually increasing their stride speed. One is geometry, the other is travel. Only the second is under the traveller's control and it remains limited. In fact, the expansion of the universe is often less like a hidden engine and more like an additional obstacle. NASA explains that the observable universe is larger than a simple light travel estimate because the universe has expanded while light was in transit, and it places the radius of the observable universe at roughly 47 billion light-years. That means even light, moving lawfully and as fast as anything can locally move, does not cross a static stage. It crosses a stage whose scale changes during the journey. For a spacecraft moving more slowly than light, the challenge is even worse. The traveller is not merely trying to reach a distant object. The traveller is trying to reach a distant object while the intervening geometry continues to evolve. In some cases, light from a distant galaxy can still reach us because of the detailed history of expansion, but that does not imply a slower spacecraft could do the same on any sensible timescale. Quite the opposite. Expansion can lengthen the route while you're still on it. The farther the target, the more the difference matters. This is where cosmic horizons become especially unforgiving. NASA says the universe's expansion is now accelerating under the influence of dark energy, and in an accelerating universe there are regions from which light emitted today will never reach us. That is not just a poetic idea, it is a practical statement about inaccessibility. If even a light signal released now from some sufficiently distant region will never arrive because the expansion outpaces the signal's ability to close the gap, then a slower spacecraft has no chance at all. A destination beyond that sort of horizon is not merely far, it is causally out of reach from our present location. So faster-than-light expansion does not hand us the keys to intergalactic travel. It can instead place parts of the cosmos permanently beyond both observation and visitation. Horizons are the universe's way of saying that expansion changes access, and not always in the direction we would prefer. Another reason the confusion persists is that human intuition likes symmetry. If space can separate two galaxies faster than light, then surely one should be able to reverse the trick and use space to bring a ship somewhere equally quickly. But the ordinary expansion of the universe offers no built-in steering wheel. It expands broadly and on large scales uniformly. It does not single out your ship, your destination, or your travel schedule. It does not contract space in front of you and expand it behind you in a controlled way. It simply changes the large-scale distance relations of the cosmos. That is why using Hubble expansion as a travel mechanism is rather like hoping the growth of a city will personally shorten your walk to work. The city can expand. Streets can multiply. Distances between neighbourhoods can change. None of that means the pavement beneath your shoes becomes a custom transport device. Cosmic expansion is a background feature of the universe, not a directional propulsion technology. Now, to be fair, general relativity does contain speculative ideas that sound more travel-friendly than ordinary cosmological expansion. NASA technical reports discussing breakthrough propulsion concepts describe wormholes as shortcuts through space-time and warp drives, as scenarios involving the expansion of space-time behind a craft and contraction in front of it. In that sense, the broad idea of changing space-time geometry to achieve effective faster-than-light travel is not nonsense invented by fiction alone. It does exist as a mathematical possibility within certain discussions of general relativity. But NASA's own material is equally clear that this is not the same as ordinary Hubble expansion, and that the required conditions are extraordinary. One NASA source notes that Alcubierre-style warp drive concepts would require large quantities of negative energy density paired with positive energy density, and another says the necessary conditions were shown to be physically unattainable. So even the most famous space-time-based travel loopholes are not consequences of the universe's everyday expansion, and are not remotely close to an engineering option at present. That distinction matters because people often hear two related ideas and quietly merge them. The universe expands. A theoretical warp drive would also involve expansion and contraction of space-time. Therefore, cosmic expansion must already be half of a warp drive. but those are different propositions. The first is an observed large-scale property of the cosmos. The second is a highly speculative engineered geometry, requiring conditions we do not know how to realize and may never be able to realize. Ordinary expansion does not gather itself into a little bubble around a ship. It does not spare the traveller from the local speed limit. It does not solve the energy problem. It does not give civilization a ready-made infrastructure for intergalactic tourism. If anything, the comparison teaches the opposite lesson. To turn expansion into a form of travel, one would need a radically controlled and exotic space-time distortion, not merely the calm large-scale stretching Hubble revealed in distant galaxies. There is another useful way to see this. Travel is about reducing the time it takes for a traveller to connect two events in space-time. Expansion does not automatically reduce that interval. In many cases, it increases the effective separation during the journey. NASA's material on the observable universe and cosmological redshift makes clear that light from remote galaxies is stretched and delayed by expansion as it crosses the universe. That means the large-scale geometry is not giving the signal a helpful push. It is modifying the route in a way the traveller must live with. A spacecraft cannot gain an advantage merely by sharing the universe with expansion, because expansion acts on the large-scale separation itself. You do not ride it so much as contend with it. That is why the edge of what we can ever see and the edge of what we could ever reach tend to move in the same philosophical direction. Expansion does not casually open doors. It quietly closes some of them. This also helps explain why cosmologists do not speak about faster-than-light recession, as though it makes the universe smaller in practice. In an ordinary map, if one point can move faster than the fastest allowed signal, perhaps distances have become cheap. But in the real expanding universe, superluminal recession is a sign that distances on the larger scales are expensive in the most absolute sense. It signals that some regions are separating so rapidly that no future intervention from here can catch them. The observer is not being handed a privilege, the observer is being shown a limit. This is one of the most important emotional corrections the subject asks us to make. The universe's ability to expand faster than light sounds at first like the beginning of a loophole. In cosmology, it is more often the beginning of a farewell. So the clean answer is this. Faster than light expansion does not imply faster than light travel, because expansion is a change in the geometry between distant regions, while travel is the motion of an object or signal through local space-time. Relativity limits the latter, not the former. Bound systems do not simply join the Hubble flow, so there is no convenient local push to exploit. Over long distances, expansion can even work against the traveller by increasing the separation during the journey. In an accelerating universe, some destinations are not merely inconvenient but fundamentally unreachable from here, and the more speculative ideas that try to turn space-time engineering into travel, such as warp drives or wormholes, are not consequences of ordinary cosmic expansion and remain deeply hypothetical, with NASA sources emphasizing requirements that are far beyond known practical physics. That leaves us in a slightly more sober but much clearer place. The universe can stretch faster than light. Einstein's rules still stand. Horizons still matter. Travel remains hard in the old-fashioned relativistic way. And if anything, the long-term trend of cosmic expansion tells a more melancholy story than a triumphant one, because on the very largest scales the future is not about easier access. It is about increasing separation. Galaxies that are now visible will not remain equally available forever, and the force driving that isolation is tied to the same late cosmic behaviour that makes the subject feel so strange in the first place. The next step, then, is to look directly at that driver and ask what dark energy means for the future of the universe and for the growing loneliness of everything that is not already close enough to stay bound together. By the time we arrive here, the expanding universe has already changed from an interesting idea into a deeply personal one, because once you learn that space can stretch and that the stretching is speeding up, the future stops looking like an endless grand tour and starts looking more like a long, quiet thinning out. That is where dark energy enters the story. It is the name astronomers give to whatever is driving the present accelerated expansion of the universe. NASA's current overview says we do not yet know what dark energy actually is, but we do know that it exists in the sense that it is the name attached to the observed speed up of cosmic expansion, and that it accounts for roughly 68 to 70% of the universe's total content. ESA's Euclid overview gives essentially the same picture, describing dark energy as part of the invisible side of the cosmos, and placing it at about 68% of the total matter-energy density. That is already a rather humbling sentence when you let it settle. Everything we usually think of as the universe, stars, planets, gas clouds, dust lanes, glowing nebulae, black holes, teacups, violin strings, unpaid bills, all of that familiar ordinary matter is only a small share of the cosmic accounting. Dark energy, whatever it is, dominates the large-scale future more than all the visible splendor ever could. And the most unsettling part is not that it is dark, because dark here does not mean sinister in any dramatic sense. It means unknown. It means we gave the mystery a label before we solved it. NASA is quite open about that. Dark energy is essentially the placeholder name for the mysterious something causing the universe to expand at an accelerating rate. And one of the live possibilities is that it could be related to vacuum energy or Einstein's cosmological constant, though NASA also lists other ideas, including changing fields, and even the possibility that our understanding of gravity on cosmic scales might need revision. The discovery itself arrived in the late 1990s, and it did not arrive politely. Astronomers had expected the expansion of the universe to be slowing down under gravity's pull, even if only gently. Instead, observations of distant Type 1a supernovae showed that those explosions were dimmer than they should have been in any non-accelerating model. NASA explains the logic very clearly. Type 1. A supernovae have a known intrinsic brightness, so by comparing how bright they ought to be with how bright they appear, astronomers can estimate distance. When those distances were compared with redshifts, the conclusion was startling. The faraway supernovae were farther away than expected, which meant cosmic expansion had sped up. The Nobel Prize in Physics in 2011 was awarded specifically for the discovery of the accelerating expansion of the universe through observations of distant supernovae, which gives some sense of how seriously the scientific community took the result. There is something almost mischievous about the way the universe revealed this. We looked for a cosmos gradually losing momentum and found one picking up speed instead. NASA's Hubble material says the universe slowed for a time after the Big Bang under gravity, but as it expanded and matter became more diluted, dark energy began to dominate and the expansion started speeding up. Another NASA page frames the same timeline by saying the acceleration began about 9 billion years after the beginning, which is to say roughly 5 to 6 billion years ago. That means dark energy is not a tiny correction arriving at the margins. On the largest scales, it is now the main influence on the long-term expansion history. Ordinary matter still matters immensely for galaxies, stars, planets, and people. But on the broadest cosmological stage, dark energy is writing the future in larger letters than gravity can erase. And this is where the loneliness of the far future begins to take shape. If dark energy continues behaving in roughly the way current evidence suggests, then the universe is likely to keep expanding forever. NASA's broad cosmic history page says exactly that in cautious terms, noting that future research may still surprise us, but that cosmologists currently suggest the universe will probably continue expanding without end. That does not mean every bound structure is torn apart. On the contrary, nearby systems held together strongly enough by gravity can resist the Hubble flow. NASA's educational material points out that the Milky Way belongs to a gravitationally bound local group that includes Andromeda, and that only sufficiently distant objects cleanly participate in the large-scale cosmic expansion. So the far future is not a story of every atom drifting into independent exile. It is a story in which bound islands remain islands while the ocean between islands keeps widening. That distinction matters because it saves us from picturing a dramatic cosmic shredding that current evidence does not require. If dark energy is close to a cosmological constant, as a good deal of present data still allows, then galaxies, solar systems, planets, and people are not expected to be ripped apart simply because the expansion continues. NASA's earlier Hubble analysis found that the observations were consistent with dark energy, having roughly the same strength in the distant past as it does now, and consistent with Einstein's cosmological constant, while also ruling out some models with rapid changes. That is not the same as proving the case closed. NASA's own dark energy overview still lists multiple competing possibilities, but it does mean the most ordinary current picture is not one in which the universe ends in a violent unbinding of all structure. It is one in which already bound systems remain together while everything not securely tied down on cosmic scales drifts farther and farther away. Now, that may sound almost comforting for a moment. The local group remains. Nearby gravity keeps its small kingdom. But then one notices the larger implication. If the expansion continues accelerating, and if our local group of galaxies stays gravitationally bound while more distant galaxies continue to recede, then the visible universe available to future observers will slowly empty out beyond that local neighbourhood. That part is an inference, but it is a very direct one from the facts we have already assembled. NASA says the expansion is accelerating and likely to continue. NISA also says the local group is gravitationally bound and that only more distant objects cleanly follow the Hubble flow. Put those together, and the long-term picture becomes hard to avoid. The galaxies that are not gravitationally tied to us will not stay conveniently placed in the sky forever. They will recede, their light will stretch, and the wider universe will become harder and harder to observe from our cosmic address. There is a peculiar sadness in that, not because the universe is being cruel, but because knowledge itself becomes more local with time. Right now we live in a fortunate era. The night sky still contains evidence of a vast cosmic web beyond our own neighbourhood. Distant galaxies are still visible. The cosmic microwave background still fills the sky. The expansion can still be measured. Future observers, in a much older universe, might not be so lucky. If acceleration continues and distant galaxies slip beyond practical reach, the sky available to those future astronomers could become far poorer in cosmological clues than ours is today. They might still infer some of the truth from local remnants and old records if such records survived, but the raw observational cosmos would be lonelier. We do not usually think of ourselves as living early enough to be privileged, but in cosmology, that may be exactly what we are, and the universe is not done being subtle here. Dark energy does not merely carry galaxies away like a careless custodian clearing a hall, it also changes the character of the light that leaves them. As expansion continues, light from remote objects is stretched to longer and longer wavelengths. NASA's Hubble material on cosmological redshift explains that light from galaxies becomes increasingly redder as it travels through the expanding universe. So the far future is not just a matter of fewer galaxies being close enough to observe, it is also a matter of their light becoming more heavily redshifted and therefore harder to detect in ordinary ways. The universe does not simply dim with distance, it also shifts. The message arrives fainter, older, and more stretched than when it began. In the long run, that makes remoteness feel less like a number and more like a kind of fading conversation. It would be tempting here to say that dark energy is a kind of anti-gravity and leave it at that. And indeed, Hubble's anniversary material says many scientists think of it in those terms, as a repelling effect that pushes galaxies apart by stretching space at an increasing pace. That picture is useful so long as it remains gentle and provisional. NASA's more careful dark energy page warns that we do not yet know whether dark energy is truly some force with negative pressure, or whether the better explanation lies in vacuum energy, a changing field, space-time defects, or even modifications to gravity itself. So one has to keep a light touch. Dark energy is what we call the driver of acceleration, not yet the final solved mechanism. The future loneliness it appears to imply is robust as long as acceleration remains real, but the deep reason behind that acceleration is still one of the major unsolved problems in physics. This uncertainty is not a flaw in the story. It is part of what makes it intellectually honest. The evidence for acceleration is strong. The late 1990s supernova results, later Hubble measurements, and ongoing cosmological surveys all point to the same broad fact that the universe is not merely expanding but doing so in an accelerated way. Yet the underlying ontology, if I may borrow one serious-sounding word for a moment, remains unsettled. NASA's Roman mission material says that understanding the origin of cosmic acceleration remains one of the most pressing unsolved problems in fundamental physics, and ESA's Euclid mission is explicitly designed to investigate the origin of that accelerating expansion and the nature of dark energy. So when we talk about the far future growing lonelier, we are leaning on a well-supported phenomenon, even while the thing behind the phenomenon remains mysterious. Meanwhile, our own cosmic neighbourhood will keep its local dramas. The local group is not frozen just because it is bound. Galaxies there still tug on one another, merge, distort, and evolve under gravity. NASA's glossary currently recognises about 80 members in the local group, while NASA's educational and Hubble materials emphasise that it is the sort of gravitationally bound structure that does not simply get carried away by the Hubble flow. So the far future is not empty in the absolute sense. It is more like a single surviving archipelago in a sea whose other islands have sailed beyond the horizon. One can imagine future astronomers in such a place still studying stars, stellar remnants, black holes, and galactic archaeology with enormous sophistication, yet with the wider cosmological context increasingly hidden from direct view. The local universe remains busy. The large-scale universe grows inaccessible. There is a quiet irony in that. Dark energy was discovered because we looked out to great distances and found a pattern in remote supernovae. The very phenomenon revealed by looking far away may eventually make far away looking less fruitful. The universe gave us just enough time, perhaps, to notice what it was doing before that very behaviour slowly concealed more of the evidence. I do not mean that in a mystical way. There is no implication that the cosmos staged a performance for our benefit, only that the timing is remarkable. We live at a moment when the universe is old enough for large-scale structure, stars, planets, and observers to exist, but not yet so old that the broad extragalactic sky has mostly slipped beyond observational usefulness. That is an extraordinary observational window to inhabit, and so dark energy leaves us with a future that is less explosive than many science fiction endings and in some ways more haunting. Not a final crash, not necessarily a dramatic tear in space-time. More likely, on current evidence, an ever-continuing expansion in which distant galaxies fade from practical reach. The cosmos outside bound structures grows sparser to the eye, and the night becomes more local with age. NASA's Cosmic History page says the most likely present expectation is expansion forever. NASA's Dark Energy page says we now finally have missions powerful enough to test what dark energy is. Euclid is already mapping the dark universe, and Roman is designed to probe the problem further. So even while the far future may be lonelier, the present is still rich with clues. We are still in the era when the universe can be read on the larger scales, and that makes the next thought almost unavoidable. If space keeps stretching, and if the sky itself will one day seem poorer than it does now, then the final thing to sit with is not only the physics of expansion, but what it means for us to live in a universe that is immense, changing, and briefly knowable from where we happen to be. By this point, the strange sentence we began with no longer sounds quite as impossible as it did at the start. Space can stretch faster than light, not because the universe is careless with its own rules, and not because Einstein left a loophole open by accident, but because distance itself can grow when space-time grows. That is the quiet shift that changes everything. the universe stops being a static room full of moving objects and becomes something more active, more flexible, and in some ways more difficult to hold in the mind all at once. Modern cosmology tells us that the universe is nearly 14 billion years old, that its oldest observable light comes from the cosmic microwave background, and that the observable universe spans about 94 billion light-years across because expansion has continued while light was on its way to us. Those facts, taken together, already ask us to think very differently about scale, history, and what it means to be somewhere in the cosmos at all. That change in perspective is, I think, one of the most interesting parts of the whole subject. We began with what sounded like a speed problem, and ended with a picture of reality that is much bigger than speed alone. The central lesson is not simply that the universe is large. Plenty of people know that in the abstract. The deeper lesson is that the universe has structure, history, and limits that do not care very much about our first intuitions. We can only see as far as light has had time to reach us. We can only see ordinary light back to the era when the universe became transparent, which is why the cosmic microwave background is called the oldest light we can observe. And because the universe has been expanding the whole while, the deep sky is not just a collection of faraway places. It is a layered record of earlier times. Looking outward is looking backward. The night is not merely distant. It is historical. There is something quietly humbling in that. Most of our daily life takes place on scales where the world seems solid, immediate, and local. We walk across rooms that do not expand under our feet. We speak to people without waiting millions of years for their reply. We live inside systems held together by gravity, electromagnetism, chemistry, memory, habit, and a schedule that often feels more pressing than the age of the universe ever could. Yet behind all of that, and far beyond it, lies a cosmos that has been unfolding for almost 14 billion years. NASA notes that humans have existed for only a few 100,000 years, while the universe has existed roughly 56,000 times longer than our species has. That is not the sort of ratio that flatters human pride. It does, however, sharpen human curiosity. It means that almost the entire story happened before we arrived, and still we have learned enough to ask how space itself changes. What makes that especially remarkable is that we did not learn it by stepping outside the universe and taking a photograph from some impossible vantage point. We learned it from light. We learned it from redshift, from spectra, from the microwave background, from distant supernovae, from patterns in galaxy clustering, from tiny temperature variations on the sky, and from the success or failure of theories when tested against observation. Light from galaxies stretches to redder wavelengths as it moves through an expanding universe, and the oldest light we can observe was imprinted when the universe was only about 380,000 years old. Even dark energy, the unknown driver of the present accelerated expansion, was not discovered by some direct handle labelled mysterious force. It was inferred because distant supernovae appeared dimmer than expected in a decelerating cosmos. Again and again, cosmology has advanced by reading faint evidence carefully, rather than by waiting for the universe to explain itself in plain language. That, to me, is part of why the subject feels both grand and intimate at once. The facts are enormous, but the method is patient. A star flickers, a spectrum shifts, a telescope gathers photons that began their journey before Earth existed. A satellite maps tiny fluctuations in ancient radiation. Out of those delicate acts of a measurement comes a story large enough to include inflation, cosmic horizons, accelerating expansion, and the likelihood that much of the universe will never be directly accessible from our position. The universe is not easy to know, but it is not wholly indifferent to being known either. It leaves traces, it writes in light, it permits inference. That may not sound dramatic in the way fiction trains us to expect, but it is dramatic enough for me. The fact that a species this young can recover a meaningful history of a universe this old is one of the most impressive things about us. At the same time, The picture is not especially comforting if what one wants is centrality. The observable universe is centered on us only in the trivial sense that every observer can see only as far as light has had time to reach them. There is no special platform reserved for the Milky Way. Our galaxy lives in the local group, a gravitationally bound neighborhood with the Andromeda Galaxy, the Triangulum Galaxy, and many dwarf companions. NASA currently recognizes some 80 members in that group. On larger scales, though, our home is just one region among countless others in a universe that is mostly dark in composition and still full of unanswered questions. Dark energy appears to make up the majority of the cosmos, and dark matter outweighs ordinary matter as well. The stars and planets that feel so substantial to us belong to the minority. We're built from the bright small fraction, and trying to understand the dim large one. There is a temptation, when faced with those scales, to turn smallness into a kind of despair. If the universe is this large, this old, and this unconcerned with our preferences, then perhaps our role is negligible. I do not think that follows. Small is not the same as meaningless. A page in a long book is still part of the book. A single evening is still part of a life. Our physical size relative to the cosmos tells us something important about scale, but it does not settle the question of significance in any simple way. In fact, one might argue that the very ability to understand any of this changes the emotional balance. The universe produced, in at least one place that we know of, beings capable of noticing expansion, measuring redshift, reconstructing the early universe, and worrying about the fate of distant galaxies. That does not make us the point of the universe. It does make us one of the ways the universe has become visible to itself, which is not nothing. And there is another part of this story that I find worth lingering over. We seem to live in a particularly informative era. The cosmic microwave background is still observable. Distant galaxies are still visible in great numbers. The expansion can still be measured. Dark energy has revealed itself strongly enough to be studied, but has not yet carried the wider universe so far into redshift and isolation that all the evidence has thinned beyond recognition. Euclid is mapping billions of galaxies across more than a third of the sky to investigate how dark energy has shaped cosmic expansion and structure, and NASA describes understanding dark energy as one of the most important scientific problems of our time. That means our moment in cosmic history is not merely late enough for stars, planets, chemistry, and life. It is also early enough for the large-scale universe to remain richly legible. Future observers in a much older universe may not have so generous a sky. That thought has a bittersweet quality I rather like. We did not arrive at the beginning, when the universe was too hot and simple for life as we know it. We did not arrive at some unimaginably remote future, when accelerated expansion may have carried much of the wider cosmos beyond practical reach. We arrived in between, late enough for complexity, early enough for evidence. The night sky available to us is not complete, but it is abundant. There are still galaxies beyond galaxies. There is still ancient radiation filling the sky. There are still patterns from the young universe preserved in ways we can measure. From one point of view, that is sheer luck. From another, it is simply where the long chain of physical conditions happen to permit beings like us to emerge and ask questions like these. Either way, it makes the present feel less ordinary than it often seems when one is distracted by laundry, emails, or a kettle that has not yet boiled. Dark energy, meanwhile, keeps the story from becoming too tidy. We know the expansion is accelerating. NASA says the universe began speeding up about 9 billion years after the Big Bang, and ESA states plainly that scientists still do not know what dark energy actually is. It may be related to vacuum energy. It may reflect something deeper about gravity. It may yet surprise us in ways our current theories do not expect. So even now, after all the progress of modern cosmology, one of the dominant features of the universe remains a named mystery rather than a solved one. There is honesty in that. Science is not a wall of finished answers. It is a growing map with clear regions, uncertain regions, and a few places where someone has written "Here be dragons" in a more professional tone. I think that matters for how we relate to the subject emotionally. A fully explained universe might be satisfying, but a partly understood universe invites a different kind of engagement. It allows wonder without superstition and humility without surrender. We are not reduced to ignorance. We are not elevated to mastery. We are somewhere in the middle, capable of real knowledge and still surrounded by questions. Inflation may explain why the universe appears so flat, and why tiny primordial fluctuations became the seeds of later structure. The cosmic microwave background may preserve the oldest light we can directly observe. Accelerated expansion may shape the far future into something lonelier than the present. And yet behind each of those achievements stand open problems about initial conditions, dark energy, quantum gravity, and the ultimate global structure of the cosmos. A good scientific picture does not end mystery, it improves it. And perhaps that is why the original question lands so well. Why space can stretch faster than light sounds at first like a contradiction. But once understood, it becomes almost the opposite. It becomes a lesson in how the universe can be deeply strange without being incoherent. Nothing locally outruns light. Causality remains intact. Einstein's rules survive. Yet the geometry of space-time is dynamic enough to let distance itself grow on vast scales in ways that our everyday intuition would never predict. The result is not a broken universe. It is a subtler one in which local law and global history fit together more elegantly than the slogan version first suggests. There is a practical lesson in that as well. Many of the deepest scientific difficulties begin when language borrowed from daily life is pushed into domains where it no longer fits comfortably. Move, distance, edge, speed, beginning. Nothing about those words is wrong, but each becomes more delicate under cosmological pressure. Does the universe have an edge? Not in the way a table has an edge. Is a distant galaxy moving away? In one useful sense, yes, but not as a cannonball moves through a room. Is the cosmic microwave background the beginning, not of everything, but of the oldest light that can travel freely to us? Does faster-than-light expansion permit faster-than-light travel? No, because expansion is not the same as local motion through space. The closer one looks, the more science becomes an exercise in careful wording, attached to careful measurement. That may sound fussy, though I think it is one of science's virtues. The universe rarely rewards sloppy categories for long. It lets them work on small matters and then quietly defeats them on large ones. Cosmology is full of those defeats, and they are often beneficial. The Earth is not the centre. The Milky Way is not the universe. The universe is not static. The visible is not the whole. Time is not the same everywhere. Space is not a passive emptiness. Distance is not always fixed. We have had to give up a number of flattering simplifications to arrive here, and I suspect that is part of what makes the current picture feel both unsettling and satisfying. It costs something to understand. Usually what it costs is a little certainty about what common sense is entitled to expect. Still, when all of that is said, the night sky remains what it has always been in one important respect. It is a source of perspective, not because it solves our private lives, and not because the stars care whether we are tired or worried or pleased with ourselves, but because scale changes thought. A universe nearly 14 billion years old, with an observable region about 94 billion light-years across, is very good at shrinking the apparent size of whatever happened at 3:30 in the afternoon. It does not erase ordinary life, it remeasures it. The same species that argues over parking spaces and loses reading glasses has also built telescopes, satellites, detectors, and theories capable of tracing the history of the cosmos back to ancient light. That contrast never stops amusing me. We are small, distractible, fragile creatures with enough insight to notice the expansion of space. So perhaps that is where I would leave it, not with a grand moral, because the universe is under no obligation to provide one, but with a kind of quiet recognition. We live in a cosmos that is expanding, accelerating, and larger than any straightforward picture can contain. We occupy one bound neighbourhood among many. Much of what exists is beyond reach, and some of it always will be. The oldest light still arrives. The distant galaxies still drift. The dark energy problem is still open. Euclid is still mapping the dark universe, and astronomers still keep reading the sky because there is more to learn. That seems to me a rather good place to be, even if it is not a central one. And now that we have spent this long evening thinking about stretched space, ancient light, and the slow widening of the cosmos, I find myself returning to the simplest part of the experience. You are here, in one small region of one galaxy and one local group, listening at one particular hour while the universe goes on, expanding whether or not anyone notices. Perhaps that is the nicest part of the whole story. The cosmos is immense and impersonal, yes, but it is also something that can be known from a chair, from a bed, from a quiet room after a long day, by someone willing to follow the evidence farther than intuition first wants to go. The expanding night is larger than us. Our place within it is undeniably small, and still for a brief while we get to ask what it is doing, and sometimes with enough patience we get an answer.